Hello, everybody. Thank you for joining us. My name is Adrian.
I'm Janie. I'm Kate.
I'm Joe.
I'm Angel.
And today we're going to talk about cryptography, the math behind encryption and decryption of secret messages. Before we jump into the letters and numbers of cryptography, we are going to talk about an integral problem to cryptography that establishes why we need it. It's called the two general problem. And in this problem, you have to imagine a valley with a castle in the middle and two armies on each side. General 1 needs to coordinate to General 2 exactly what time they need to attack. Our issue for cryptography is that the messenger General 1 sends can be intercepted by the castle. And that arises our first question of cryptography. How do we keep the castle from being able to read our message? And the answer, in general, is encryption. And so with encryption, it also arises a new question. If we get the encrypted messages to the second army, how can they read it? And for the answer in cryptography, it's decryption. So through encryption and decryption, we have our basis for cryptography. And we, in the modern age and back when we first started with cryptography, utilize different forms of math. And here's the first.
Okay, so modular arithmetic. So basically, modular arithmetic is an arithmetic system that focuses on integers. And so usually in modular arithmetic, values will repeat based on like certain integers. Okay, so modular arithmetic is based on something called modulo operations. And basically what that is that it indicates that you need to divide and then take the remainder off of it. So there's not really per se a quotient. So the structure goes, there's a dividend, which is A, then we have mod, or it could also be called modulus, and it indicates the action of dividing and taking the remainder. B is our divisor and R is our remainder. So to further go on top of that, we have an example. So I have 7 mod for 3. So when 7 is divided by 4, that would be a remainder of 3. That being said, we have to further see and understand it. So we have integers 0 to 14 down here on this number line. And on top, this is supposed to represent mod 4. So as you can see, there's sort of a pattern going on and it repeats. Well, the reason why we have 0, 1, 2, 3 is because, like I said before, the way that this is structured, it's A, mod, B, and then a remainder. So B is our divisor. So we're kind of, in this setting, we're dividing by 4. So if we were to go here, and we were supposed to do 4 divided by 4, we would get a remainder of 0. And if we did 5 divided by 4, we would get a remainder of 1, and so on. And like I said earlier, that like modular arithmetic, when you values will repeat or reset when you get to like a certain integer. So like, for example, 8, if we were to do 8 divided by 4, we would get 2 and it'd start over at 0. Okay. Then we're going to go further with that, and we have multiplication. So it's pretty simple. All you have to multiply is this area. So it's just parentheses A times B, parentheses mod C, and then remainder. So here's an example. So there's A will be 4, B will be 7, 6 will be 6, and we don't know our remainder, and that's what we're looking for. Okay, so all we're doing is grabbing the formula and then plugging them in, and all we're doing is a multiplication problem right here. So it would be 28 mod 6. So that's basically, remember, mod indicates that you need to divide and take the remainder. So you would do 28 divided by 6, and you get 4. Okay. So then there's modular congruence. So let's assume that these are two operations. So we have A subset 1, we have A1 mod B remainder, A2 mod B remainder. So let's say that these two B's have the exact same number and these two R's have the exact same numbers too. Okay, so out of that, we can assume that A1 and A2 are congruent to one another in mod B. So then it would be set up like this. A is congruent to B in mod N. So to further see that, I have a problem. So I have 11 mod 4 and 7 mod 4. So you can already see that these two are the exact same. So that basically proves that like right now 11 and 7 are in the same mod 4. Then when we like go ahead and use the operation to divide, so be 11 divided by 4, get a remainder of 3, 7 divided by 4, get a remainder of 3. So we already have, they already share the same remainder. So from here, we can already conclude that 7 is congruent to 11 and mod 4. Then I'm going to pass on to Adrian.
So utilizing modular arithmetic, we can establish one of our first basic ciphers. These are ciphers that can be done both by humans and by machines. And our overarching version of this is going to be the substitution cipher. One of the most famous substitution ciphers is the Caesar cipher, and it can be illustrated by this image. You have your original set of inputs, the alphabet, and the entire alphabet is shifted. So in this example, it's shifted by 3 spaces. E goes to B, D goes to A, C goes to Z. You're substituting in letters. And there is some math behind this. First off, we're going to set a few labels, because just like computers, cryptography is easier for humans if we can associate letters with numbers. So first, let's do A to 0 and Z to 25. We're not going to do A to 1 and Z to 26, because when we're using modular arithmetic, as established earlier, when we establish a set, instead of starting at 1, because you can have a remainder of 0, when doing modular arithmetic, you start your set at 0. Before we jump into equations, let's establish a few variables. Lowercase p is going to be our letter that's being encrypted. Lowercase k is going to be the key. That's our shift factor. So in the slide before, when we shifted our alphabet by 3, that means that lowercase k is equal to 3. And our lowercase c is going to be the resulting encrypted letter. It's whatever is spat out. So when we put in E and we got B, that was our encrypted letter. Now we have the actual equations. So to encrypt in the Caesar cipher, we take P plus K, so our letter being encrypted, and we add it to the key. And then we take that sum and plug it into mod 26. We divide by 26, take the remainder. And then we map it out onto our graph once again, and that will give us our resulting letter. And to decrypt, you just do the reverse. You take C, our encrypted letter, subtract the key, and then divide by 26, take the remainder, find it on the chart, and you have your original encrypted letter. And so we're going to use an example. So we have our chart once again as our reference point, and we're going to let our message be zinc and let k equal 21. We're going to shift the alphabet forward 21 spaces. So the first step is to identify each letter's numerical value. So Z25, I8, N13, and C2. And then we lay out the equation. So we have their numerical values on the left, and then we have K as 21. Then we have our modular function with 26. And so we're going to take the sum. So for the example, we're going to do Z first. Z is 25. We add 21. That gives us a total of 46. The issue is that there's not 46 letters in the alphabet. That's why we use modular arithmetic. We divide 46 by 26, and we get a remainder of 20. So we go onto our chart, and we find 20, and 20 is connected to U. So Z is encrypted into U. You repeat that 4 times, and zinc with a K of 21 becomes UDIX.
Okay, so speaking of substitution ciphers, we have the German Enigma, which was used by the Nazis during the war. It's kind of like a typewriter, so you could type in your message, and for each letter you type in, a new letter will light up, like shown in that picture. So inside the Enigma, first there's these rotors, and each rotor is a wheel with all the different letters on it, and they each will substitute the letter you typed in. So it goes through each of the rotors, each time becoming a different letter. And so we have the plug board, and it's important because if a code breaker guessed the positions of the rotors, they could just type in the message and decrypt it pretty easily. And the plug board is just there to swap out different letters. And it's pretty hard to try to guess like all the different letters that could be swapped because you could substitute all of them or you could substitute none. So it just makes it more complicated and a lot harder to decrypt. So now we're going to talk about just how many combinations did the plug board add to the Enigma. And first you need to choose notation. So this is n, choose k. So you have n objects and you want to choose k. And it's just used to figure out how many different combinations of k you can choose from n. And it's a simplified way of writing n factorial divided by k factorial times n minus k factorial. So let's say you just wanted to substitute two different letters. So you have 26 letters overall, and you want to choose which two to swap out for each other. You do 26 factorial divided by 2 factorial times 24 factorial, which is just a simplified way of writing that. Okay, so now we're going to actually start trying to solve this. So first of all, you could just not swap out any letters, and there's only one way to do that. And then you could just use one wire, so you're swapping out two letters, and that would be 26 choose 2, which is equal to 325. And then let's say you wanted to use two wires. First of all, you have 26 letters, you choose 2 for the first wire, and then after you use those 2, you only have 24 options left, and you just multiply those and get 89,700. So I just continued that for the rest of up to 13 different wires. So you don't have to try to read all this, obviously, but this is what I just showed you. So 0, 1, and 2 different wires. And I continued that until I got to 2, choose 2. So you have no more options left. And then I just wrote the answer to each of those. But then I ran into a problem because let's say I substituted A for B and then C for D. Whenever you're doing the math, that it counts it different whenever you do C and D and then A and B. So they're the same combinations of letters, just in a different order. So that's going to count that as 2 combinations when it's really just 1 combination. So you have to do some dividing. So let's say you have 2 wires, you're going to do 89,700 because we figured out a moment ago that that's how many combinations there are for 2 different wires, and we divide that by 2 factorial, which is 44,850, and you just continue that. So you divide it by the number of wires factorial. And so now you're going to add all those together, and you get about 500 trillion different combinations that the plug board added. And if you were to go through all of those one by one and just try to figure out all the different combinations, it would take about 10 billion years, so they had to figure out new ways to decrypt messages.
An integral part of cryptography is understanding prime numbers, like 2, 3, 5, 7, and so on, whose only factors are 1 and itself. Numbers that aren't prime can be factored into prime numbers, and smaller numbers are easy to see, like 18 is 2 times 3 times 3. Euclid's fundamental theorem of arithmetic says that every number is either prime or can be written as a product of primes, and that each number has one unique prime factorization. Since there are infinite primes, we can choose 2 large prime numbers to multiply together to create a composite number whose factorization is difficult to figure out. When the numbers get really big, just as it's difficult for us to solve, computers actually have a hard time solving them as well, which helps to create a secure system. Up until now, we've been talking about encryption systems designed to be encrypted and decrypted by humans. Computer encryption works a little bit differently. To a human, the phrase "hello there" is read as 2 words, 5 letters each, with a space in between. However, to a computer, that phrase is interpreted as a series of zeros and ones called binary. That binary is representative of a number, in this case, 87 septillion and then some. And this means that messages are really just numbers encrypted as other numbers.
So the Raven cryptosystem is a modern computer encryption system that relies on prime numbers and modular arithmetic to function. The way it works is to pick two large prime numbers, p and q, that are both congruent to 3 in mod 4. Those primes are multiplied together to give a value that we're going to call n. And n is what's called a public key, which is something that is made publicly available and allows anyone to encrypt messages in the system. To do so, you simply take the message you wish to encrypt and take m squared mod n, which will be the ciphertext. And you might wonder why this system is secure. If there's a simple formula for encrypting a message, can't it be easily reversed? Well, it turns out it's not so easy. One of the quirks of working in modular arithmetic is that knowing the factors of the mod number opens up additional possibilities. So if we're working in mod 77, we have more options if we know that 77 is equal to 7 times 11.
An example of something that we can only do if we know the factors of the mod number is decrypting the Raven encryption system. So let's take the formula that we used to find our ciphertext in the beginning. C equals m squared mod n. We can rewrite that slightly differently. What this is telling us is that c is the remainder when you divide m squared by n. That means that c plus some multiple of n is equal to m squared. And the k, as long as it's an integer, that will be a multiple of n. From there, we can plug in p times q for n, because that's where we got n in the first place. And we can rewrite it two slightly different ways. C plus an integer times q, and c plus an integer times p. And you'll notice that looks a lot like what we had up here. And that's because these are really just a different way of saying that c is congruent to m squared in mod q, and c is congruent to m squared in mod p. So we started off working in mod n, and we ended up working in mod p and q. And this is going to help us finish decrypting the Raven crypto system. But first, we have to talk about the idea of multiplicative inverses. So in normal arithmetic, an inverse is just something that you multiply a number by to get back to 1. So a and 1 over a are inverses. But in modular arithmetic, we don't have access to fractions. We can only use integers. We still have inverses, and we'll denote them by a sub 1, or whatever value a is. So a times a sub 1 is congruent to 1, I should say, in mod x. That might not make a lot of sense, but hopefully this example will make some more sense. So if we're working in mod 7, then 5 and 3 are going to be inverses, because when you multiply them together to get 15, take 15, divide by 7, you have a remainder of 1. 7 times 2 is 14. You have a remainder of 1 between 14 and 15. If we change the mod that we are working in, 5 and 3 would both have different inverses. So it's dependent on what mod number you're working with. So let's go back to the two congruency statements we had earlier. We want to find a value of c that satisfies both of these statements. But before we can create that value, we're going to define two inverses. The first one is p sub 1, and that's going to be the inverse of p when we're working in mod q. And the second one is q sub 1, which will be the inverse of q when we're working in mod p. The formula we're going to use to find a value of c that satisfies both of these equations is c is congruent to m squared times p sub 1 plus m squared times q sub 1 in mod n, or pq. I just left it as pq. So to show that that formula works to satisfy both of these equations over here, we're going to do some math. So first thing we do is we simplify the mod down to just one of the factors. We established earlier we're allowed to do that. From there, you'll notice that this first term has p as one of its factors. And since we're working in mod p, and we're adding to this term over here, a term that has p as one of the factors, we're not really changing the value. If you're working in mod p and you add p, that's just going to get divided away. The congruency statement will still be true. So we can really just get rid of this guy over here. And that leaves us with c is congruent to mq times q sub 1 in mod p. If you remember to the slide before this, q times q sub 1 is defined as being congruent to 1 when we're working in mod p. So we're multiplying m squared by 1, so we can just get rid of that too. And we're left with one of the equations we wanted to prove was true. And to prove the other one, we do almost the exact same thing, except for instead of working in mod P, we're working in mod Q. But it goes much the same way. And we see that we get the second equation we were looking for. So the formula up top satisfies both equations. Time for a quick example. Let's say we were working with P equals 7 and Q equals 11, and we received the ciphertext 24. We find P sub 1 using that, and Q sub 1, we get 8 and 3. And then we can plug everything into the equation. So the ciphertext we got needs to be congruent to m squared times 7 times 8 plus m squared times 11 times 3, all in mod 77. So we simplify that down a couple of times, one more time, and we're left with this. And from here, the way to solve this is to find a value of k such that 24 plus 77k over 89 is both an integer and a perfect square. And unfortunately, the easiest way to do that is to use a computer. It's hard to do that by hand. There is a slightly more complicated way of decrypting this system that doesn't require any computers, but that takes much longer to explain. It's a little bit more complicated. But I hope this gave you an insight into why modular arithmetic is very useful in encryption. Just as a brief summary, the Raven encrypto system, anyone with the public key can encrypt messages, but only someone with P and Q can decrypt them. And finding P and Q is hard, because as Janie was talking about earlier, for very large numbers, finding those two prime factors can be very difficult, even for computers.
So in conclusion, there are multiple fields in math where some of the greatest breakthroughs are by bringing other fields of math in. But cryptography is based on using multiple fields of math, whether it be prime numbers, modular arithmetic, combinatorics, and the such, across basic and modern ciphers that humans or computers can use. And in the end, it's really for the same cause: security and anonymity when it comes to creating codes. So we'd like to say thank you to our advisor, Yvonne, to the Chaos Theory group who helped us with our presentation, and to the entire math department, as well as our live studio audience and those watching at home.
From viewers like you. Thank you.
Thank you.
Thank you.
Okay, so there's more math groups start at 5:30. If y'all want to go to that, but you can also stick around and ask questions since nobody else is presenting in here.
Thank you.
Thanks, everybody.
Thank you guys. Thank you for watching. Yay.
I'll stop recording. Please stop.
Thank you, everybody in the chat.
Yeah, if anybody in the chat wants to ask a question, you can.
All right, so just before we get started, we want to say thank you for coming to our presentation today. And we just want to get right into it. So our group decided to pose you all with a question. So as you see on the screen, there are 4 different terms, and we want you to guess the 5th one. So I'm going to give you guys like 30 seconds or so to think to yourself, think in your head, or talk amongst the people and guess what comes next. Don't tell us though, but think about it. All right, so if you guessed 3, 1, 1, 2, you are correct. And if you don't understand, no worries, we're gonna go into it quite shortly. But that brings us to our topic today. So we are descriptive sequences. I'm Aria.
I'm Iris.
I'm Mia.
And I'm Simran.
And today we're going to go over what descriptive sequences are, how they work, some of the hypotheses, some examples, and stuff like that. So how does it work? So in our first term today, we have 1. And so in order to determine the next term, you just must describe. So we would just simply say that there is 1, 1, making the next term 1, 1. And as you see now, we're just going to count it 1, 2. So we would say that there are 2 1s, making your next term 2, 1. And for this one, we would say that there are 1, 1, 1, 2. And bringing you back to what we had at the beginning as your example, we're just going to circle this and we separate it so that there's the 1s over here, the 2s over here. And we see that there are 1, 2, 3 1s and 1, 2. So you just simply write 3, 1, 1, 2. And we're going to do it one more time. So we see that there are 2 1s, 1, 2, and 1, 3. So you would just write 2, 1, 1, 2, 1, 3. So right here, we are using our little key we wrote. So we have the green as the descriptor and the red as the digit being described. We like to call it our little Christmas tree because it looks like a Christmas tree. And we're going to do another example just so we can get it all like in our heads and stuff. All right, so this is a much bigger number, so prepare yourself. No. All right, so we see that there is 1, 0, 1, 2, 1, 3, and 1, 4. So you simply just write 1, 0, 1, 2, 1, 3, and 1, 4. And if you ever get confused, you can look up here and you see it's just exactly what I'm saying. So we have it written out in a word form and then just as the digit. And so you can just say 1, 0, 1, 2, 1, 3, and 1, 4. So now we're just going to describe it one more time. And this is where it gets a little confusing. You don't want to miscount or else it'll just throw your entire sequence off. So we'd say that there's 1, 0, then there's 1, 2, 3, 4 1s, 1, 2, 1, 3, and 1, 4. Making your next term 1, 0, 4, 1, 1, 2, 1, 3, and 1, 4. So now we're just going to describe this one more time. So we see that there's 1, 0, 1, 2, 3, 4, 5 1s, 1, 2, 1, 3, and there are 2 4s. Making our next term 1, 0, 5 1s, 1, 2, 1, 3, 2 4s. And just like what I'm saying is all the way up here. We're just going to describe it one more time. So we see that there's 1, 0, 1, 2, 3, 4 1s, 2 2s, 1, 3, 1, 4, and 1, 5. So you just simply write it as 1, 0, 4, 1, 2 2s, 1, 3, 1, 4, and 1, 5. Once again, we have our little Christmas tree. It's a little thicker this time because we have more numbers. And this just kind of just shows you guys how we're describing it with the little code over there. So this brings us to our definition that we came up with. So descriptive sequences are constructed by listing the amount of times each digit 0 through 9 appears in a given term in ascending order to produce the next term. So essentially, each term describes the prior term. Bringing us to,
Will these sequences ever come to an end? Because if you keep just describing a number, can you ever stop describing a number? So let's just take a look at that first example that we had up on the board when you guys walked in. So we're just going to continue it out and just continue it out. So you see it keeps describing itself, right? Continue it out. And let's describe this one together. All right. So we see there's 2 1s. I see 3 2s. And there are 2 3s. And there's 1 4. So if we just click out the next term, look, they're identical. So this term will keep repeating itself because it'll keep describing itself. So this is when we say we end the sequence, because otherwise you're just going to get a long list of the same term over and over. So when there's a repeat, we just say we end it. And here are just some more examples. Here's 13. We see it'll end with that repeat. Here's 44. We say it ends with that repeat. And here's 5. Again, it ends with that repeat. So you can do this for any natural number, 0 and on, as long as they're whole numbers and they're not negatives.
Okay, so in order to construct these sequences, we came up with a few general rules to follow. So let's look at our first one, and that is that the order of the first term is completely irrelevant to what the rest of the sequence is going to look like. So if we start with 15, for example, we're going to come to right here where we have this self-describing term at the end. But if we take this first term and switch those digits around to be 51, it's going to be exactly the same after the first term. So as you can see, those will be identical. And we have one more example of 203 versus 320. And if you look at everything from the second term on, they're exactly identical. Now let's look at our second rule. So this is about zeros. We're going to describe zeros as they appear but we're not going to use them to describe any other terms or digits in this. So with 203, we would say there is 1 0, there is 1 2, and there is 1 3. What we're not going to do is this. We're not going to say there's 1 0, 1 2, 1 3, and then 0 of every other digit, because that would add them in later. Because once we put them in there, it's going to say one of each of those afterwards. And that's kind of contradicting the whole point of this, because then we're describing numbers that aren't there. So we're no longer describing the same number. So we're just going to not do that. We're only going to describe the zeros as they appear, never use them to describe anything else. And that brings us to our third rule, which is the way the digits in a term are arranged is important. So we said the first term, the order does not matter at all. For the other ones, it does. So for example, if we start with 1 5 7 2, we're going to describe the numbers in counting order or ascending order. So we start with 1, then 2, then 5, then 7, giving us 1 1, 1 2, 1 5, 1 7. We're not going to do it like this in the order they appear or in any other order other than counting order. And that brings us to our last rule, which is that a sequence is always going to come to either a self-describing term or a repeating cycle of terms. So if we look at 6 and 53, we can see they both come to a single self-describing term. But if we look at 600, we're going to see there's actually 3 different numbers here at the end that we have color-coded for you. And if we go and describe the blue one, we get the green one. If we describe the green one, we get the yellow one. If we describe the yellow one, we get back to the blue one, which this number and this number, they're exactly the same. So this sequence of numbers, this cycle, is going to keep repeating itself over and over and over. So we're going to have the same 3 numbers repeating forever. So for these ones, that's when we say it's going to end, is when we have a repeat in the set of numbers. And then we can see this again in 57, also with 3 repeating terms.
So where did we start out with this? It was pretty wacky. We worked out all the numbers from 1 to 100 by hand in our notebooks. And if you want to see what that looks like, it kind of looks like this and that and all of that and all of that. These are only a few pages from our notebooks. So kind of we're crazy people. And when we did this, we had to do it all by hand. So we were taking our time to make sure we weren't making any human errors. And when we did this, we realized that some cycles don't end in only a single self-describing term. Sometimes they end in that repeating cycle of terms. And at first, when we saw this pattern, we were like, we're doing something wrong because it wasn't ending. But then upon closer examination, we found that it was just repeating the same numbers over and over. So we put this in form of a hypothesis. Starting points at or above 46 are going to repeat a cycle of terms rather than a single self-describing term, unless they reflect a term that's prior to 46 or they contain a 0. And we're going to talk about zeros later. So here's just an example of this. So we see 45, which is before 46, ends in a single self-describing term. We see 46, which is 46, so it'll end in that repeating cycle of terms. We see 47, which is above 46, so it'll end in that repeating cycle of terms. And we've already talked about 15 and 51, but we're just going to talk about them again. So 15 is before 46, so it'll end in that single self-describing term. 51 is a reflection of 15, which is before 46, so it'll also end in that single self-describing term. Here's just a box to show you where the cycle actually starts to reflect. That's great. But where do we go from there? Well, zeros weren't included in that hypothesis. So what happens with the zeros? We tried to find a pattern with that. So we each took a set from 100 to 900, 1,000 to 9,000, 10,000 to 90,000, and 100,000 to 900,000, and we worked those sequences out. And here are just some examples of what those look like. And we were trying to find patterns while doing this. And here's some from set 2. and here's some from set 3. And while we're doing this, we're just trying to figure out, is there a pattern?
And so each member of our group was assigned a set. And while we were working through the sets, we were finding really similar patterns. And so we came together and we formed a hypothesis. And the hypothesis was that if a number ends with 0, on and after the third line, it will start with the digit pair of 1, 0. So this is the hypothesis in words. So let's go through this. So let's get a number from set 1. So I chose 600. We need to note that this whole presentation, we have been looking at either repeating cycle of terms or single self-describing terms, meaning we have been focusing on the endpoints of the terms. We are now transitioning from that to just focusing on the first 2 digits of each term. So does this satisfy our hypothesis? Yes, because on and after the third line, it does start with a digit pair of 1, 0. So let's get a number from set 2. We chose 2000. Again, it also starts with 1, 0 on and after the third line, thus satisfying our hypothesis. So set 1 and 2 are working. So let's get a number from set 3. We get a number from set 3. Here's 30,000, and again, on and after the third line, it does start with 1, 0. So is there a pattern? Yes, there is a pattern. All these numbers, all these different sets have come together. On and after the third line, it does start with a digit pair of 1, 0. But you may recall that we said 4 sets. So let's get a number from the set 4. So let's try the biggest number, 900,000. So here's 900,000. Does it start with 1, 0 on and after a third line? Yes, but we have a problem. Everything was going fine. Set 1, 2, and 3 were working, and we reached 900,000. It does start with 1, 0 on and after a third line, but we reach lines 12 and 13, and it goes from 1, 0 to 2, 0. And you might be asking yourself, why does 2, 0 appear? And the reason why is because there are 10 ones in this line, right? Because there are 10 ones, there's 1, 0, and then there's 10 ones. So when we're describing this line, we now have 2 zeros in place. So now we have to say there's 2 zeros, thus breaking our whole hypothesis just because of 900,000. Broke everything.
Okay, so let's take a look at prime numbers now, since that last one didn't work. So we looked at all the prime numbers up to 199 and then a whole bunch more. And we came up with this, that any sequence where the first term is a prime number containing the digit 3 is going to come to a single self-describing term and not a cycle of terms. So we're going to start with 3, which is obviously our lowest prime number that has 3 in it. So we can see right here, it does come to a single self-describing term. And if we look at 163, we can see that again. And also in a slightly bigger example of 1123, same thing. So these all work. And our hypothesis is going great. But let's look at what happens when we introduce a 0 into our first term. We're going to look at my new least favorite number, 307, where we see we have a cycle of 2 terms that repeat. So the addition of a 0 into the first term of our sequence contradicted our hypothesis and completely threw everything off. So yeah, we don't like zeros, they are our enemies. So again, the hypothesis was incorrect. And actually every hypothesis that we've come up with since has completely fallen apart when we introduce a starting term that has a 0 in it. So because zeros crushed our souls, we thought we'd lighten the mood with a little fun fact. And so this is the degenerate sequence. It's 22 or 2-2. And as you can see, there's 2 2s and 22. So right off the bat, it's going to describe itself. This is the term that only has 2 digits and still describes itself. This is the only one. And there are no terms that have fewer digits and still describe themselves. And the only terms that we found that describe themselves have at least 8 digits in it. So this one is on its own, but I thought that was kind of cool. So
All right, so coming to the end of our presentation, we're going to go over the summary. So we've explained what descriptive sequences are, we've given you like a little cute definition we created. We went over some general rules. We explained our research process and took you through our hypotheses. But most importantly, we've shown that not all mathematics are complicated and that sometimes rules don't apply to everything. So for example, in most fields of math, you're always looking for a pattern or a rule to be true. But for descriptive sequences, we concluded that it is boundless without overarching patterns. For example, we would come up with a hypothesis and then some number like 0 or 900,000 would just ruin everything, which goes to prove that not all math is set in stone. So we just want to thank you guys, and we'd like to thank our advisor, Evan, for being awesome. Math Rob, the entire math department, our peers, RNG for watching everything we've done over and over. And of course, you all for coming to our presentation today. So thank you.
Thank you guys so much. Awesome. Amazing.
Great, welcome to our presentation. My name is William.
My name is Devin.
And my name is Ivan.
And today we'll be discussing non-Euclidean geometry and specifically elliptic geometry.
So first, I'd like you to imagine that you're in Washington and you need to get to Moscow immediately, as in right now. So you hop in your single person private jet, and now it's up to you to decide, are you going to take route A, which is more of a straight line from Washington straight to Moscow, or are you going to take route B, which is more of an arc between the 2 points? So please hold on to your answer and see if it changes after we introduce you to the magic of elliptic geometry.
Before we get into non-Euclidean and elliptic geometry, we must first understand what Euclidean geometry is. And while you may not be familiar with the term, I believe most people are familiar with the basic concepts because it is the geometry taught in school. So it's based on 5 main postulates. I'm going to quickly go over those. The first 2 postulates talk about what a line and line segment are. So if you draw a line between 2 points, you get a line segment. And if you extend that line segment, you have a line. The third postulate says if you draw a circle with through a line segment, you can use one of the points as a center, and you can use the line segment as the radius. The fourth postulate just says that all right angles are equal, and the fifth postulate, which is a key difference between non-Euclidean and Euclidean geometry, says that when you have a point and a line with the point not on the line, there's always one parallel line. And this is known as the parallel postulate. It is a key difference between non-Euclidean and Euclidean geometry because it was never proven as a theorem, which means that there are different possibilities such as no parallel lines and infinite parallel lines. This is non-Euclidean geometry, and the 2 main types are hyperbolic and elliptic. Before we get more into elliptic geometry, a key term we need to define is curvature, the amount in which a curve diverges from a straight line or curved surface from a plane. We can see that in this image right here. In Euclidean space, we have a flat plane with straight lines. However, in elliptic space, we have curved lines that curve toward each other, which means they'll never be parallel lines. And the sum of the interior angles of a triangle in elliptic space will be greater than 180 degrees. And we will prove both of these things later.
So the main focus of our presentation is going to be about elliptic geometry, which is a subset of non-Euclidean geometry that has a positive curvature. And it replaces Euclid's parallel postulate with the idea that no parallel lines can exist. What this means is that any 2 lines will always, on an elliptical surface, will always intersect at least 1 point. And throughout this presentation, we're mostly going to be using the surface as a sphere as our model. So here's just a visualization of a sphere with 3 lines on it. And these 3 lines will form 6 different points and on like different sides of the sphere. And one of these 3 points will form a triangle. And this triangle differs from normal Euclidean triangles in that it's like slightly curved. And we're going to be talking about this more on a later slide. So spherical geometry is the study of the 2D surface of a sphere, and it's very similar to elliptic geometry. In fact, it's sometimes referenced to as double elliptic geometry, and this is because 2 points on a spherical geometry, instead of only intersecting at least 1 point, will always intersect at 2 points. And this is because in a spherical model, we're going to be defining a point as a pair of antipolar points and a line as a great circle. A great circle is basically any line that completely separates the sphere into like 2 equal halves, or encompasses the greatest diameter of the sphere. And an antipolar point is basically just points are on the directly opposite sides of the sphere. So you can just imagine the south pole and the north pole of the Earth. And here's just a picture that shows antipolar points with 2 great circles that just completely bisects the Earth into the sphere into 2 equal halves. And here's just a direct application of spherical geometry using the model of the lines of longitude and latitude. As you can see, the lines of longitudes will always completely bisect the Earth into 2 equal halves, which makes them great circles. Meanwhile, the lines of latitudes are going to be considered small circles, which is basically just any line that doesn't bisect the Earth into 2 equal halves or encompasses the greatest diameter of the Earth. However, there's the exception of the equator, which is also considered to be a great circle, and that's because it splits the Earth basically into 2 equal halves.
Great. So next we are going to prove that there are no parallel lines in elliptic space. Before we get into these axioms, we need to remember and redefine lines and points in this space. So just remember that in elliptic space, we don't have straight lines. Instead, the lines are great circles, and that we always use antipodal points and a pair of antipodal points. You just remember the north and south pole for reference when you want to remember antipodal points, because they're on opposite sides of the sphere.
So we have to redefine points and lines, a point as a pair of antipolar points and a line as a great circle in order to prove that there are no parallel lines in elliptic geometry. And we'll be doing this by going through the axioms of incidence, betweenness, and separation, which will allow us to solidify the idea of a unique great circle. So first, the axioms of incidence basically states that given two distinct points, A and B, there will be a line L that forms the incidence between these 2 points. And I just like explain the axioms of incidence in a Euclidean context, and I'm going to move this over to a non-Euclidean context. So as we just said earlier, we're going to be redefining a point as a pair of antipolar points, which means which just mean P sub 1, which will be a pair of antipolar points, and Q sub 1 and Q sub 2, which will be another pair of antipolar points. So these 2 pairs of points will be distinct, which means that P sub 1 will not be equal to Q sub 1, and P sub 2 will not be equal to Q sub 2. And given these 2 pairs of points, there will be a unique great circle C. And it's kind of hard to visualize this, and it's just a 2D diagram, so we're going to be showing a 3D diagram of a unique great circle. So as you see, these 2 pairs of antipolar points will form a unique great circle C. However, if you were to add a third pair of antipolar points, it has to rest on this unique great circle. Or else you're going to have a completely different unique great circle in order to compass it. So like something like that.
So next, we're going to look at the axioms of betweenness, represented by this really cool equation right here. Don't worry, this doesn't have anything to do with multiplication. All this means is that point B is in between point A and C. And point B is also in between point C and point A. So if we look at this in a Euclidean context, it still holds. As you can see, B is clearly in between A and C, and B is still in between C and A. But now we're going to try to look at it in an elliptic context. Point B is in between A and C, but if you think about it, isn't point C also in between B and A? And isn't point A also in between C and B? That leads us into our next axiom, which is the axiom of separation.
So as he said earlier, the axioms of betweenness is ill-defined in elliptic space, and that's because since C is technically between B and A is between B and C. So this is why we need to exchange this in relation with the axioms of separation, which is right here. This diagram may look confusing, but we're mainly going to be focusing on points A, B, C, and D. So this notion right here, it basically just states that if points A and B separate C and D, then points A and C cannot separate B and D. And that might also just sound confusing, but I'm going to explain this right here. So as you can see, in order for you to cross from points C to points D, you have to always go through either A or points B. However, if you want to go from B to D, then you can just go from this path right here instead of going, so you don't have to cross to A or C. And here's a 3D visualization of it of the great circle on the sphere. So we needed to go through all three of these axioms, as we said earlier, to solidify the idea of a unique great circle. And as we said earlier, we're equating a line to a great circle. So since two unique lines will always form like incidence on an Euclidean space, we're just saying that given two unique great circles on an elliptic space, and since we're using a sphere, you can see that they'll always intercept at one point or another, which allows us to show that there are no parallel lines in elliptic geometry.
So due to the nature of elliptic geometry, even the most basic things, such as shapes, have different properties that we have to relearn, such as the way they're formed. Triangles, for example, in Euclidean geometry, is formed by creating straight lines to connect 3 points. That's the fastest way to connect a triangle in traditional Euclidean geometry. However, there are no straight lines in elliptic geometry. Instead, the fastest way to form a triangle is using arcs of the great circle. Some other cool properties that triangles in in elliptic geometry have are two sides combined are always greater than a third alone. The sum of the interior angles is always greater than 180 degrees. And cosine of A times cosine of B equals cosine of C instead of the Pythagorean theorem. So just to recap, this is what a triangle on the surface of a sphere looks like. As you can see, due to the curvature, it kind of has a bent along the surface of the sphere. That affects a bunch of the properties, and it's really interesting to look at. So next I'm going to prove why the Pythagorean theorem doesn't hold in elliptic geometry. So the way I'm going to do this is I'm going to use proof by contradiction. That means that I'm going to pretend that it does work to show that it doesn't. So like I said, let's assume that it does work. So now we have spherical triangle F with 3 vertices, A, B, and C. And each of them has a right angle. And according to Euclid's 4th postulate, all right angles are congruent. So the arc length of each side is given by the equation S equals R theta, where R is the radius and theta is the angle of the arc. So since the radius and the angle measurements are uniform throughout the sphere, each angle subtends the same arc length. So there's no way that A squared plus B squared could equal C squared. Thus, we just showed that the Pythagorean theorem doesn't hold in elliptic geometry. Here's another triangle to look at in elliptic geometry, and each of them have the same arc length. So if we try to do the Pythagorean theorem with this, we will be saying that 1.12 squared plus 1.12 squared would equal 1.12 squared. But that just doesn't make sense. This is just showing us why the Pythagorean theorem doesn't hold in elliptic geometry.
Great. The next thing we're going to prove is that the sum of the interior angles of a spherical triangle is always greater than 180 degrees. To do that, we're first going to understand what a lune is. A lune is just the area enclosed between 2 circular arcs, with the arcs being part of great circles. So this is a 2D image, and here's a 3D image of what a lune is. Simply put, it is a wedge of a sphere, just a fraction of the surface area. But in this proof, we're going to define a lune as a wedge of a sphere with angle theta, and the area is represented by L theta. Next, we're going to take a look at the picture for the proof. And this has a spherical triangle on it. And we're going to point a few things out before we get into the equations. First of all, and this is obvious, we have a sphere, so we know we're working with elliptic geometry and that this is a spherical triangle. The spherical triangle has 3 angles, alpha, beta, and gamma. And these 3 angles form 6 lunes on this sphere. This may be hard to visualize, but you can see that the dark gray parts here, these are the lunes of angle alpha. And if you look closely, the lunes of beta would be going here and here, and the lune of gamma would be here and here. So hopefully you can better visualize that there are 6 lunes on this sphere. And these 6 lunes we know cover the entire sphere, which means they encompass the entire surface area. So the area of the 6 lunes equal to the surface area of the sphere. However, since the ends of the lunes do not meet, but instead they overlap, we have to count the extra area in which they are overlapping. And that is the area of the triangle. So we will actually be adding 4 times the area of the triangle on top of the surface area of the sphere. And this is probably the most difficult part to understand, so I'll try to explain it clearly. If the triangle is part of lune alpha, we will count it once, and it will be the same time as counting like any part that's not part of the triangle and the rest of the sphere, and this will all be part of the surface area of the sphere. However, we see that we have to count it again for the lune beta and lune gamma. So we have to count the area of the triangle 2 extra times on top of the surface area of the sphere. Now, the reason we count it 4 extra times for this equation instead of just 2 is because the lunes intersect in 2 different parts of the sphere. Once in the front and once in the back, which means there are 2 identical spherical triangles. And if we count the area of this triangle 2 extra times, we have to count the area of this triangle 2 extra times. So therefore, we will count this area of the triangle 4 extra times. All right, now we can put this into an equation. So the surface area of the sphere, which is 4 pi r squared, with r being the radius of the sphere, plus 4 times the area of the triangle is equal to the 6 lunes. If we factor out a 2 on both sides and divide by 2, we get that 2 pi r squared plus 2 times the area of this triangle is equal to just 3 lunes, 1 for each angle. Here we can substitute this formula in for L as the area of the lune. Before I do that, I'm going to first derive this formula just to show that I didn't make it up. So when we look at the picture of a lune, we see that no matter how we rotate it on this sphere, it will always remain the same shape, size, and area. What this means is that the area of the lune, the proportion of the area of the lune to the area of the sphere is equal to the proportion between the lune's angle theta and 2 pi, which is the maximum angle on a circle. When we solve for L here, we multiply both sides by 4 pi r squared, so theta over 2 pi times 4 pi r squared. If we divide 4 pi by 2 pi, we just get 2, so we end up with 2 theta r squared for the area of the lune. So that is where this formula comes from. Great, now we can substitute it in, and we get this on the right side of the equation right here. And we see we can factor out a 2r squared here. We divide both sides by 2r squared. We end up with this final equation. The sum of the interior angles of this triangle, alpha plus beta plus gamma, is equal to pi radians, which is 180 degrees, plus the area of the triangle divided by r squared. So we come to the conclusion that the sum of the angles is equal to pi, 180 degrees, plus the area of the triangle divided by r squared, which cannot be 0. And we know this cannot be 0 because if this equals 0, then the numerator, which is the area of the triangle, will be 0. If the area of the triangle was 0, then we wouldn't have a triangle, so that wouldn't work. Therefore, this, which is positive and greater than 0, would be added on to pi, which is 180. Therefore, the triangle, the sum of the interior angles of the triangle will be greater than 180 degrees.
So now we get to look at some really cool applications of elliptic geometry. So the one that we're going to start with is navigation. Because the Earth is a sphere, you can use elliptic geometry for navigation to find the fastest way to get from point A to point B. Pilots and GPS systems utilize elliptic geometry to maximize fuel and time efficiency all the time. So back to the situation at hand. Do you remember which route you chose? Well, hopefully after going over elliptic geometry, you chose route B, As you can see, Route B is almost 1,500 kilometers shorter than Route A. And that's because Route B utilizes the arcs of the Great Circle instead of a straight line that might have worked in Euclidean geometry, but not when we're talking about the surface of the Earth.
All right, so another application of spherical elliptic geometry is in the field of astronomy. And there is a branch of astronomy called spherical astronomy. The idea of that is the universe around the Earth is known as what's called a celestial sphere. And with this celestial sphere, you can develop a celestial coordinate system, which you can use to locate celestial bodies like planets and stars at unknown distances. And you can locate them at a specific time, date, and from a specific location on Earth. In the past, it was used for religious and astrological purposes, but it's now even still used for timekeeping and navigation, because as you know, humans have been using the stars for navigation for a very long time. All right, so to come full circle, some key concepts to remember are that parallel postulate and curvature divides geometry into different types.
And also important to keep in mind that elliptic geometry is a geometry for a positive curve, no parallax, and the sum of all interior angles of the triangle will always be greater than 180 degrees.
And that elliptic geometry is very useful in the fields of navigation and astronomy. And with that, we would like to thank the GSC math instructors for having an awesome time this semester, and everybody who came out here to support us. Thank you.
Okay, so you may be wondering how such a complex topic in math can relate to such a movie like Run Lola Run. So in order to make that connection, first we need to define the word chaos. So in the dictionary, chaos is defined as complete disorder and confusion. But in terms of physics, chaos is defined as behavior so unpredictable as to appear random owing to great sensitivity to small changes in the initial conditions. So in our discussion of chaos theory, we will be paying more attention to the definition in terms of physics, because in chaos theory, chaos, the word really is misleading. It's not truly unpredictable. Nothing's truly unpredictable if you have perfect information, but we'll explain this later. So this poses the question of, so what is chaos theory really trying to prove? So I hope we can answer that question for y'all as we go through our presentation. So chaos theory is really the attempt to develop an equation or formula for seemingly chaotic sequences that are sensitive to initial conditions. And chaos theory is really only applicable for equations or situations that change as time goes on, which are also known as dynamical systems. It is also very dependent upon initial conditions of a system. And it's the idea that if you slightly change these initial conditions, it can completely cause your results to be drastically changed by a lot. So a good example of this is the double pendulum. So a double pendulum is where a pendulum is on the bottom of another pendulum. And as in this video, we have 3 pendulums starting at almost the same spot, but their starting positions are differing by the slightest decimal place. As you can see, after just a few seconds, the pendulums have started to separate and their paths have started going their own ways. So the blue pendulum right here has completely gone askew from where the red and the green, and now the red and green are starting to separate. This shows that as time goes on in a dynamical system, it is easier to predict outcomes towards the very beginning where not much time has passed. But if you try and predict things way ahead in the future, like say for weather, like for 2 weeks in advance, it'd be much harder to predict that weather than if you're trying to predict the weather maybe 5 minutes from now. So this is just a good illustration of how dynamic systems as time go on make it harder and harder to predict the outcomes of the situations.
So an important concept to understand before things get too chaotic are fractals. And fractals are never ending recursive patterns, which just means they use the outputs for the next input, which infinitely repeats itself and demonstrates self-similarity on different scales. So they exemplify self-similarity, and self-similarity is just something that repeats itself exactly or roughly the same pattern on different scales. And two examples are the Sierpinski triangle, which repeats itself exactly the same on smaller scales. And then like in things like nature, coastlines and snowflakes repeat roughly the same pattern, but they're not all exactly the same. So snowflakes are all composed of ice crystals, water vapor, and dust, but snowflakes are somehow all unique, and we want to know why. So snowflakes differ because they all have different initial conditions that are never repeated the exact same in the atmosphere. And they're the picture of chaos and how the initial conditions affect the outcomes, because each snowflake is different and is never repeated.
So some of y'all may have seen this fractal before. It's called the Sierpinski carpet, but today in our presentation, we'll be constructing one for you to get a better idea of what self-similarity is. So at the very beginning, we start with just a blank square. Nothing special about it. It's just a square. So then we move on to the second step where it is divided into 9 equal subunits. And with fractals, you want to take the middle piece out of the fractal after dividing into 9 equal subunits. So we will take this pattern and use it for and repeat it as we go into smaller and smaller scales. So on the next slide, we'll see that we use the same pattern to divide the first square into even smaller pieces. And we continue this pattern forever and ever. It never ends. But for time's sake, we're just going to stop right here because we could be here all day. So anyway, we have an equation for self-similarity. And so self-similarity is really the idea that part of a shape is similar to the whole size of the shape. And it shows the same statistical properties at multiple scales. So for the different variables, N represents the number of equal subunits. R is the scaling ratio. And then the D represents the number of dimensions that the fractal has. And so we're going to use this equation, and we're going to give an example to satisfy that the equation always has to equal 1. So here, this should look familiar. This is the second step of constructing the Sierpinski carpet, and it has 9 equal subunits, and it is a 2-dimensional figure. So then we'll just take those numbers and plug them into our equation to get 9 times r squared equals 1. And so from here on, it's just divide and take the square root. So you'll divide by 9 on both sides and get r squared is equal to 1/9. And then after that, you'll take the square root of both sides to get r is equal to 1/3. So you may be wondering, or we know that r is the scale ratio, but you may be wondering how that really relates. So we'll go back to our Sierpinski carpet. So right here, we have a total side of just 1, but it is divided into 3 smaller sides. So as we take a look at that scale, or the ratio between the entire square itself and the 3 equal subunits is 1:3. But that could also be written as a fraction as 1/3, which satisfies the self-similarity equation.
So the easiest way to understand how fractals have a relationship with chaos is understanding that fractals are like a screenshot of how initial conditions have complex outcomes. And it's easy to see because they're still images. And if people are able to visualize them in a static sense, it's a lot easier to understand in regards to dynamical systems, which are just systems that change as time continues on. So attractors are really important to understand the Lorentz system, which we'll talk about later in the presentation. But an attractor on a graph is a set of conditions that a dynamic system tends to be attracted to. Like, for example, if you and your both love like to hang out at the gym, chances are your attractor is going to be between the gym and the quad, because let's be honest, that's the only place we can go. And attractors themselves are fractals, but we like to also call them attractors.
Okay, so here's the Lorentz system of equations, and we'll dive deeper into this in a minute. But as you can see, there are 2 different attractors, which the arrows point to, where the values are attracted to. These two attractors are types of strange attractors, which are also fractals themselves. So there's a connection between those attractors and fractals.
So Edward Lorenz was a meteorologist who wanted to study weather patterns, and he created this system called the Lorenz system, which is the best way to demonstrate chaos and its unpredictability. So he started with 3 initial similar conditions, and as the graph continued, the 3 equations that were like a decimal point off grew further and further apart, and they never crossed each other's paths, which like parallels left, because things can never happen the same or be completely predicted, because every initial condition is never known.
So since Edward Lorenz was a meteorologist, he wanted to model convection currents. So he derived the Lorenz system of differential equations. And within these equations, there's a variables x, y, z, hence why this system sits within a 3D plane. And then initial conditions are inputted into those variables to create a graph like this. Okay, so the dynamical system that is chaos can be described geometrically as motion on an attractor. And there are 3 components to that attractor. There's a point, which is where like the initial conditions start. There's closed loops, which are periodic cycles, and then there's tori, which are combinations of those periodic cycles. So the residing like principle among like the Lorenz system is convection currents. So convection currents simply means hot air rises and cold air sinks. But there's also additional factors that need to be taken into account. So the hot air in the atmosphere is actually a lot of times cooled, so it'll sink because it's more dense. And then the cold air at the bottom is heated by the ground, and it'll rise because it's less dense and because like become heated. So like the rotation between the 2 different air temperatures is what Lorenz really specifically wanted to study. Okay, so now we'll apply this to the Malchus water wheel. And the Malchus water wheel is unlike a regular water wheel, which like rotates in the same direction at the same speed. The buckets in the Malchus water wheel actually have holes at the bottom of them, which like have water coming out of them. It makes the system like behave in an unpredictable manner. And also this is an inverse model of convection currents. So the water being poured into the buckets is considered heat. And the heat, when the water is like, when the bucket is filled, it goes down instead of in a regular conventional convection current, it would be pushed up. And also the water leaking from the bottom of the buckets is considered the cold air, or the air that is losing heat radiation. So as we see here, it looks like the wheel is starting at the same point, but as time continues, the wheels like behave in like an unpredictable manner, and they begin to oscillate back and forth and like change directions and speed. So the Lorenz system of differential equations perfectly models the chaotic motion of the Malchus water wheel. As we see the water wheels at the top, they differ in initial conditions. So the first one is 1 degree from the vertical, and the second one is 2 degrees from the vertical. And you can see the centers of mass being like starting to like be like, drawn in the middle. And those like center of mass like have to come from 3 different numbers. So the first 2 numbers come from the coordinate of the center of gravity, and the third number comes from the angular velocity, which is the rate at which the wheel is rotating. So with those 3 numbers, we can start plotting how these systems are going to behave. And as time continues, you can see the trajectories change a lot, but at the beginning they look rather similar, but you can see like just the tiny change in the initial condition, how different the systems look. So now we can finally look at the Lorenz system of differential equations. Since the Lorenz system is governed by convection currents, it should make sense that the variables within these equations have to do with convection currents. So x is the rate of convection, y is the horizontal temperature difference, and then z is the vertical temperature difference. So before we can analyze these any further, we need to know what a derivative is. And a derivative is simply the rate of change of a system with respect to time. So if we take a curve or a part of the system and take a point on that curve and find the slope, also known as the tangent line, we see if the slope is either positive or negative. And if the slope is negative,
the system is decreasing. And then if the slope is positive, the system is increasing. So now we can read the like different equations as how is x changing with respect to time, how is y changing with respect to time, and how is z changing with respect to time. And these circled values are parameters, and these are constant throughout the whole equation. These parameters have to remain the same. You can't like put in like 9 for lowercase sigma, or else the system will like no longer resemble the Lorentz the way the Lorentz system is graphed. So for little sigma we have 10, for r we have 28, and for b we have 8/3. Okay, so now we can see the Lorentz system of equations into action. So at the top right, we have the equations, and then further to the right, we have the different parameters that we'll mess with in just a second. And at the bottom right, we have the different initial conditions. And right now we only have solution A going. And for solution A, we have 0 for x, 1 for y, and then 20 for z. And we can see in the middle, we have a 3D graph of the system with x, y, and z axes. And then over to the left, we have a 2-dimensional plane. And where the x-axis would normally be, we have time. And then where the y-axis would normally be, we have the x, y, and z variables. So we're seeing how these different variables are changing with respect to time. So at the top, we have z, which is kind of behaving on its own. And then we have y and x, which they're kind of behaving similarly. So as one changes, the other also changes. And I think that's also interesting is you can see the attractor moving along the system as time passes. And also we have another initial condition at the bottom called solution B. And this condition, like initial condition, is super similar to solution A. However, it differs by 100th of a decimal point. So the x and y's are the same, or the x and z's are the same, but the y changes from 1 to 1.01. And now you can see how the systems at the beginning, they look quite similar. But as time progresses, the systems diverge and don't look the same at all. So, and then now if we like manipulate the parameters, so if you look to the second parameter, we have 28, but in a second it'll input 10, and you'll see like the system is no longer resembles that like almost figure 8 like curvature. It'll like look like a spiral. And the x, y, and z variables, or like the different initial conditions, don't really change. The systems follow each other, so it's hard to see like the blue from the red. And so it just travels between 2 fixed points. And we even put in 15, which is closer to 28, and it still looks like that. But then we put 20 in, which is now even closer to 28, and it starts to resemble the Lorentz system. And if we put in 28.1, which is super close to 28, it looks like the original system that we had.
So another equation or formula that is exemplary of the principles of chaos theory is the time series and logistic equation. So in this equation, we have 3 variables, x sub t, k, and x sub t plus 1. The k value represents the net birth and death rate. So this value is always between 0 and 4, and this value is constant, just like the lowercase sigma and the r and the b in the Lorentz system. And the x is representative of the percentage of carrying capacity being occupied. For carrying capacity, let's say Shelby has a carrying capacity of 100,000 people and 20,000 people live there. The x would be 0.2. It's a percentage, so it's never going to be below 0 or above 1. And the x sub t plus 1 means it's what the population is going to be at the next time interval. This is at the current time interval, and this is at the next time interval. Let's look at it in action. So here's the same formula, and we have k equals 0.95 and x equals 0.4. When we plug it in, we see that this is a recursive formula. This is just like fractals. You take your output and you plug it in for your next input. And this system just keeps repeating itself, as you can see there. Now, if we look at it on a graph, we can see even more information about it. Now, we look at the x-axis, make sure we see that's time, and the y-axis is the population x. And we can see that when k equals 0.95, it will attract towards 0. You see the points are getting closer and closer to 0. That's true for any k value below 1. It will always attract towards 0. And if we look at this quadratic recursive graph, we got to see that the x-axis is x and the y-axis is the next x, or the x sub t plus 1. And we see how we take the 0.4, we plug in and get the 0.228, and do that with the same points over there. And I'll talk more about that later. And now look for k equals 1.4, and we see how it attracts towards about 0.29. And we can see similarly how it affects this graph and how it's a lot steeper of a curve, and how it has a higher population at most points. Now let's look more in depth at this graph. So the x value is the inputs and the y value is the outputs. We start out with 0.4. That's our initial population. And we plug that in and we get 0.228. So we go up here and graph this point. Now we move over to the identity line, the y equals x line, because that shows how, or that shows like the output is the next input. That shows that pattern. So we take that and we plug in the y value for the next x value, and we get 0.167. So we come down here and graph it right there. And we just continue this process on and on until we've graphed this entire equation. Now let's look at more k values. Whenever k is above 3, there are multiple attractors. So we can see here there's 2 different attractors. This system is moving towards 2 different values. And we can see when we change it slightly, just by 0.1, there becomes 4 attractors. Let's look at that more in depth in this graph. So we can see down here, when k equals 3.4, there are 2 attractors. We can see one at the bottom right here, and the same pattern is happening at the top. But can you see how it narrows out and it begins to look more and more like a line? Now, if we look at 3.5, that pattern doesn't exist. It looks more like a cosine or a sine function, because there's a top, there's the crest and the trough, and those are 2 separate attractors. Now this is the recursive, or this is the recursive graph for that 3.4 value. And we can see how whenever we graph that same sort of system, and the parabola goes above the identity line, we have to go around in a spiral sort of pattern. So let's look at more k values. Whenever k is above 3.57, it begins to act chaotically because there are no attractors. So you can see that none of these terms repeat ever. You can also see that in this graph. This looks similar to the double pendulum effect because they start the same place with slightly different initial conditions, and they begin to resemble the same pattern. But as time progresses, it becomes less accurate, and they tend to diverge as time goes on. So that just shows how slight changes in initial conditions can just change the outcome farther in time you get. So in summary, chaos theory is not one simple idea that you can apply to one idea, to one thing. It's an umbrella term. It describes many different things. It mainly focuses on the initial conditions of a system. If we have perfect information, we can predict everything. However, we don't have perfect information. Our technology can limit us. Like when I was doing those calculations, the calculator only goes down 10 decimal points. There's obviously more decimal points than that. So if I'm trying to predict like years and years in the future, it's going to be less accurate because I won't be able to use all those decimal points. So yeah, that's chaos theory.
So we'd like to thank Vaughn for instructing us, the math department, the cryptography group, to listen to our presentation like 500 times, Governor School East, and y'all for coming.
So good. Do the beginning of, I know this is sort of crazy, but do y'all want to do the beginning of your presentation for anyone that missed it?
It was like one
This
slide.
one was way worse for me.
It was like
It's literally the first slide that we were unmuted,
Okay.
or we were muted.
Yeah, I don't
So
Dang, that was my
it's
fault.
literally just him
It's
saying.
just me. I'm good.
I don't
I'm
mind.
chilling.
You don't mind?
I don't mind. I just want slide. Encore?
Yeah.
Okay. Wait, you see what I do?
Share.
Wasn't it just like the first slide?
Yeah. Well, when did we unmute, Yvonne? Was it like, I think it was like the second or third slide.
It was on the chaos.
That was
but
so
it's
smart.
the definition of
No, my
chaos.
voice.
Oh, so it's like just the first slide.
Yeah, just the
Oh,
run.
okay.
This is.
Okay, so we just like start from the beginning. Wait, you're playing rock, paper, scissors. Have you ever tried to play rock, paper, scissors with someone through this? It's impossible. Oh, yeah,
Yeah, we're
okay.
This is chaos theory.
Wait, is it gonna say it's recording? Is it recording?
It's still recording.
It's
Oh,
still
still recording,
recording,
my bad.
so,
Okay.
but be normal.
Okay. Good afternoon, everyone. My name is Eli,
I'm Cooper.
I'm Mallory.
I'm in Stewart.
and we'll be presenting chaos theory to you all today. So chaos theory may be a new term to some of y'all, but I'm sure as Governor School E students, you remember the hit movie Run Lola Run. Now, this movie is very exemplary of chaos theory in terms of the butterfly effect. Now, at the beginning of the movie, when she's starting her adventures, she runs down the stairwell and passes by the dog and the boy. And the first time, the dog barks at her and she goes about her day. The second time she runs down the stairs, the boy trips her, and that changes everything that happens after that. And the third time, she runs down there and the boy and the dog don't do anything and she screams at them. And that's a whole nother timeline. So each day there were 3 different conditions at the beginning, 3 different initial conditions. And that changed the rest of her day.
Keep going, are we good?
Good afternoon, and in case I don't see you, good evening, good night, good morning, and welcome to All Things Sugar, Spice, and Golden Ratio and Ice. I'm Rebecca.
I'm Amrita.
I'm Aaliyah. I'm Kanaya.
Sorry about this. So first we'll start with an introduction to the golden ratio, including its equation and demonstration of it. Next, we'll move on to give some brief info of the Fibonacci sequence and the golden Bible before we move on to how the golden ratio is applied to art, architecture, nature, and the human face. Last, we'll talk about our perception experiment with how mass play a role and how our facial features are perceived differently with the golden ratio.
So according to Alfred S. Passamentier and Ingmar Lehmann, the golden ratio refers to the division of a given line segment into a unique ratio that gives us an aesthetically pleasing proportion. Not just limited to the area of mathematics, it can be found in many other areas, including the human body, nature, art, architecture, among many other things.
So for a visual of the golden ratio, imagine you have a piece of yarn and you cut it unequally. The whole segment before you cut it would equal A plus B, but the longer segment would be A and the shorter segment would be B. So the ratio of A over B should be equal to A plus B over A. And both of the ratios should equal 1.618. And this symbol is phi, which just is a symbol for the golden ratio. So in simple terms, the ratio of the longer segment to the shorter segment should be equal to the whole segment over the longer segment.
This is the golden ratio equation where phi equals 1 plus the square root of 5 over 2. Like Rebecca said before in her slide, the long segment over the short segment equals the whole segment over the long segment. To simplify it more, since we are using a lot of variables in this one, we can say instead the long segment over 1 minus x, which is b, is going to equal 1, the whole segment, even though the whole segment can be any number over the long segment. We just chose 1. And then we just cross multiply to get the quadratic form, x squared plus x minus 1.
We'll then take that quadratic equation, put it into a quadratic formula, and get 2 solutions. One being read as -1 plus the square root of 5 over 2, and the other one is -1 subtract the square root of 5 over 2. So we take the positive one because the negative solution is a measurement that we cannot use. However, we also use the positive solution because it's basically the inverse of 5. 1 over x equals 1.618. And so 1 over 1.618 equals x, which is the inverse, basically the solution here. And then we'll flip it on the other side to get the actual answer of 5.
And then we'll also multiply it by its conjugate, which basically changes the signs between the binomials -1 and the square root of 5. And so we can also get the square root, the radical out of the denominator because we can't have that. And so once we multiply by its conjugate, we get -2 subtract 2 to the square root of 5 over -4. Divide the whole thing by -2. And here we have the golden ratio here.
The Fibonacci sequence is something that you'll hear frequently throughout the slides, and it's a series of numbers in which the number is the sum of the two before it. So for example, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, so on and so forth. And the correlation it has with the golden ratio is that when a Fibonacci number is divided by the one before it, the quotient approaches the golden ratio. So here you can see that in this corner, the quotient isn't really close to the golden ratio, but here it has the same 4 digits. And every time you divide it, like if you further divided it, these digits would get closer to the golden ratio.
So now let's demonstrate the golden ratio in terms of the golden rectangle. So you first start off with a 1 inch by 1 inch square. Then you add on another square that has side lengths of the greatest side length of the previous rectangle. In this case, you just have the 1 inch by 1 inch square, so you add on another 1 inch by 1 inch square. Together, these two squares make a 2 inch by 1 inch rectangle. The greatest side length of this would be 2 inches. So you add another 2 inch by 2 inch square over here. And then together, these squares make up a 3 inch by 2 inch rectangle, of which the greatest side length is 3. So you add on a 3 inch by 3 inch square, and this pattern goes on infinitely, either in terms of getting smaller or bigger, but approaching the golden rectangle and approximately the golden ratio of 1.618. So let's take the bigger square, 8 inch by 8 inch square, for example. The ratio of its longer segment to shorter segment, 5/3, is approximately the same as the ratio of its whole segment, 8, to its longer segment, 5, which are both approximately equal to 1.618. So this directly relates to the Fibonacci series because the dimensions of each square equals the sum of the dimensions of the previous two squares. And this is the golden spiral, which is achieved when you take that golden rectangle diagram and you draw an arc in each square connecting all of them. We'll discuss about the presence of the golden spiral in different areas in life throughout the presentation.
Okay, so first we'll talk about how the golden ratio is used in art and photography. In 15th and 16th centuries of the Renaissance era, the golden ratio was known to artists as the divine proportion, and so they used it in their paintings to make them aesthetically pleasing. So well-known artists who used the divine proportion include Leonardo da Vinci, Michelangelo, and Raphael. And here's some examples of paintings that use the Fibonacci spiral, which basically they're aligned to the golden ratio. And including examples such as Da Vinci's Mona Lisa, Mondrian's Red, Blue, and Yellow, and the Great Wave. Now, the slide graded is basically a visualization of the golden ratio, which is based on a combination of smaller rectangles with the ratio of 1 to 0.618 to 1. And you'll see that the rectangle here in the middle is a little bit more bunched up, so that way we can have the exact proportions of the golden ratio. And so if we take this picture here and apply the slide grade to it, it's more balanced out as the sun is completely in the top right corner. The dirt is just below this line here, and the grass is just in the middle. So everything is just balanced out, and not too much is being shown. And here are some other examples, such as this building here is just along this line here, and the clouds are just in the middle of the top line and the bottom line, so it's completely balanced out.
So now let's discuss the golden ratio's presence in architecture. The golden ratio is a fundamental principle in architecture. In order to design and construct an aesthetically pleasing structure, there's a variety of requirements that need to be taken into consideration. The golden ratio's general uses in architecture include balancing equilibrium, attractiveness, scaling, and its application to various shapes. For example, a building would need a good sense of balance since people naturally gravitate to such buildings. And this concept would actually be accomplished by basing the structure off of the principles of the golden rectangle, what I talked about before. So these are some of the famous structures that have the golden ratio in its designs, including the Great Pyramids, Notre Dame, Taj Mahal. But one of the most famous structures in the world, and the one we most associate with the golden ratio, is the Parthenon, especially since the ancient Greeks placed so much emphasis on the special quality of the golden ratio due to its repeated appearances in nature. That's why we chose to dissect how the Parthenon has the golden ratio appearing in its layouts, as opposed to all the other famous structures that we mentioned. So some quick facts about the Parthenon. It was a symbol of the Athenian Empire's supremacy and power. It was built in the 5th century BC. It was constructed by Phidias, Callicrates, and Inictinus. And as you can see here, Phi is actually named after one of the constructors of the Parthenon. And the golden ratio is found in many of the Parthenon's layouts. So this, as you see with the diagram on the right, it's a quick overview of the exterior of the Parthenon that reflects evidence of the application of the golden ratio in its design. As you can see here, the rectangles and the ratios that it mentions to its left all correlate with the 1.618 golden ratio. This is just a quick overview since we don't have time to go into all of where the golden ratio appears in the Parthenon. However, there's a lot of debate around the intentional versus accidental use of golden ratio in architecture, especially in the Parthenon. And this is furthered because there's no historical records of the original plans of the Parthenon. But the golden ratio's presence is undeniable. It was voted the world's most beautiful building in 2016, the Parthenon, and it was renowned for its quality of having been built to last. And it can be inferred that the golden ratio played an important role in this, since some of its main functions are to maintain proportionality and keep a sense of balance and equilibrium in the structure. So overall, the golden ratio plays a significant role in making buildings aesthetically pleasing and ensuring it is sturdy with the right sense of balance. So it doesn't matter if it was accidental or intentional, because the golden ratio's presence, having been brought about in either circumstance, really served to make the structure shine, in both in terms of its physical beauty and actual strength.
Many times you'll see the golden ratio in nature and you won't realize it. This picture, you see that there's 13 spirals clockwise on the bottom of the pine cone and 8 counterclockwise. The DNA molecule is a double helix spiral, and it's measured in angstroms, which is a unit of length that's equal to 0.1 of a nanometer, which is also 10 to the negative 10th power. And the length of it is 34 angstroms and the width is 21. And 34 divided by 21 is 1.619, which is very close to the golden ratio, 1.618. In the top 2 examples, you'll see the golden spiral and the seashell and the hurricane eye, but also the golden spiral appears in flower seeds, which are in the center of the flower. And the Fibonacci numbers most of the time correlate with flower petals. So for example, the daisy has 8 petals and the buttercup has 5 petals. And also, no one really knows if the golden ratio in nature is accidental or intentional, because there's no history of when it was like first recognized or deemed the golden ratio.
Human face. How to find the golden ratio on the face? Well, not like this. Scientists create a mathematical formula to see why people are considered beautiful, and this was through measurements. First, you have to consider the length and the width of the face, and divide the length by the width. For an aesthetically pleasing face, it should equal about 1.6 millimeters. Second is the hairline to between the eyes, and from between the eyes to the bottom of the nose, and from the bottom of the nose to the bottom of the chin. This should all be equal. Lastly, the length of an ear should equal the length of the nose, and the width of an eye should equal the distance between the eyes.
That mask though. So we did a perception experiment evaluating how masks affect our perception of one's facial features. And we had a female subject and a male subject. And we wanted to identify if the participants would draw something that correlated to the golden ratio without telling them anything about it.
So to carry out our experiment, we held an elective in Math Rob's room with 36 participants. The instructions you see here on the board are the exact instructions our participants saw. So we told them that there are two pictures in front of them. One is of a girl with her mask on, and the other is of a boy with his mask on. We asked them to please draw on the mask to show how they think the rest of their facial features would look like. We told them no complex art is required, just a 30-second to 1 minute sketch will do. However, we gave them two big requirements. We needed them to include where they think the nose will end, as well as where they think the lips are positioned. For the nose, we just were looking for something like a triangle or a curve to indicate where it ended. But for the lips, we did want something realistic, something like that. The sizing was up to them. However, we would like to emphasize again that we told them nothing about drawing the golden ratio.
After our lecture, we took some data and we made some measurements. We did 3 fixed measurements and 4 variable measurements. Our first measurement is the hairline to the top of the mask. The second one is the hairline to the bottom of the mask. So the first one was hairline to the bottom, top of the mask, sorry. And the last one is mid-eye to the top of the mask. And the variable measurements include top of mask to bottom of nose, the bottom of nose to top lip, the top lip to the bottom lip, and the bottom lip to the bottom of the mask.
And I would like to reiterate that the fixed measurements are fixed because they're set measurements on a person's face, not affected by the participants' drawings, while the variable measurements are affected by the participants' drawings.
Here are some examples of what people perceive the male and female to look like. We do want to say a quick disclaimer about human error. We do appreciate that people came out to participate in our experiment, but their drawing skills could take into account of how they actually wanted to draw the lips and the nose. So we may not see exactly how they want to perceive the female and male's face to look like. Our group also hand measured each measurement, so we also could make a human error, but we tried to prevent any major errors. For example, the male's original measurement from top mask to bottom mask was 96. So we allowed ourselves to have a 93 to 99 error room.
So after our elective, we had some uncertainty about like how we were going to evaluate the data and if the golden ratio would appear. In the end, some of our analysis didn't have a pattern or didn't correlate to the golden ratio.
When we started looking at the data, we looked for results that was close to 5 and 2 times 5, which shows that it is exactly like making proportional adjustments to measurements. We also look for 1/5 that shows that taking the inverse can get you close to 5.
So then we started to analyze our data. We took all of our measurements and we put it into a big spreadsheet and we started experimenting with a lot of ratios. In total, we experimented with over like 25 different ratios to get close to the golden ratio. An example of a ratio we tested out was from the hairline to the bottom of the nose divided by the bottom of the nose to the bottom of the mask. And to account for human error, since not all of our participants were artists, we deemed that 0.1 above or below the golden ratio would be approximate to the golden ratio. Some of the major calculations we did included taking averages, looking at the golden ratio frequencies in a certain ratio, and looking at the closest results to 1.618. We compared all of these calculations among the data for the same person as well as between the two different people. So the closest ratio to 5 we found, the closest overall and the closest in the male's data, was from the bottom of the lip to the bottom of the mask divided by the bottom of the nose to the bottom of the lip. This had an average about 1.56, which was actually only 0.0559 away from 5, which is really great. We actually got this ratio after experimenting with its inverse first. So bottom of nose to bottom of lip divided by bottom of lip to bottom of mask. When looking at that, we saw the averages and the results are really close to 1/5. So we thought, how about we take the inverse to see if that results correlate with 5, and it did. And what you see here is a visual representation of the ratio that we tested out. However, there were some interesting observations to this ratio. First of all, its significance was not reflected in the female's data. In fact, she had an average of about 1.277 So not really close to 1.56 at all. And we kind of inferred that this perhaps reflects different perceptions of the golden ratio in regard to gender. Another important thing to note that this particular ratio had a relatively low golden ratio frequency of only appearing around 8 out of 36 times, while the second closest ratio to phi in the male's data had numbers approximate to the golden ratio appearing around 24 out of 36 times. So very interesting. Another thing to note, however, is that the frequencies for the male and female in this particular ratio were close to each other, 6 versus 8.
All right, ding, ding, ding. So this was the measurement that was the most frequent and pretty close to the golden ratio. And the measurement was the mid-eye to bottom of nose over top of mask to bottom of nose. It occurred 27 times in the female and 24 times in the male. And the average for the female was 1.71, sorry. And the male average was 1.72, but both were about 0.1 away from the golden ratio, 1.618.
Data for top of mask to bottom of nose divided by the mid-eye to the top of mask were not so great, as the female's average is 1.45 and the male's average is 1.47, which is not really close to the golden ratio. Frequencies for the female were 11 out of 36, and the male's frequencies were 10 out of 36 for the golden ratio.
However, we would like to say that we included this in our presentation because even though they didn't see the golden ratio, the participants did see a certain ratio, seeing as how the frequencies and the averages are pretty close to each other.
Our closest results to phi for the female was 1 with 4 phi, and for the male, there was 2 close ones. One that's exactly like the females, and the second one has 4 really close to phi, and 1 exactly like phi.
So some notable points to mention to kind of sum up our experiment, other than the significant ratios that we showed you, were that only a few ratios of all the different ones we tested out were actually relevant to the golden ratio. At least 2 of them, results approximate to phi, did not appear, and the females and males data did not yield the same results for the most part. One ratio even had a mixture of phi and 2 times phi for the female. So we think that this kind of emphasizes that we don't perceive all of the ratios of the face in accordance with phi, which brings us to our key question again. Was the presence of the phi in the people's drawings accidental or intentional?
And we wanted to end with a note like the golden ratio makes things beautiful, but it doesn't define all beauty. Everything is beautiful in its own way. And we would like to say thank you to our math instructors, our research advisor, Math Rob, you guys, our audience face-to-face, and our audience over Zoom. And thank you to everyone who made GSE possible.
Thank you so much.
All right, we have time for, are there any questions?
Why do you think there was a big, oh, go ahead. I'm sorry, I was worried. Go ahead.
Do you think that the reason that the males could have been different from the females because the male had one of those like big masks and the female looked like she had like the one I'm wearing?
Yeah, so that is some interesting, that's an interesting observation that we point out. There's obviously much room for improvement in our experiment and variables to think about. I think particularly that mask was a little bit bigger, but also his face was also quite long. Sorry. But yeah, there's definitely things to think about. Definitely ways to make this experiment better. Thank you for pointing that out.
So do you think, like, can you think of the reason why there was such like a big difference between the female and male?
So we think that the golden ratio, we think that there's a difference. There may be a difference how like you expect a male's face to look a certain way and a female's face to look a certain way. And we think that people see different golden ratios in different parts of the face for male and female. That's why we think we saw that, but we would need to do more testing in order to really determine that and eliminate some of those loose variables that Ali was talking about.
Hi everyone, and welcome to our presentation. Today we'll be talking about hyperbolic geometry, which is a form of non-Euclidean geometry. My name is Nisha.
I'm Aaliyah.
I'm Krista.
And I'm Isa.
So in order to get a good understanding of what hyperbolic geometry looks like, we can first look at a cylinder in a Euclidean plane. So we all know that a cylinder is made up of two circles, one on the top and bottom, with infinitely many line segments in between. But what would happen if we altered one of the line segments, let's say the line segment A to B, and slid it over all the way to the left? You can see here that the sides of the cylinder curve inward to form what we call a hyperboloid. And this is a key figure in hyperbolic geometry. So like I mentioned earlier, hyperbolic geometry is a form of non-Euclidean geometry. And in order to understand what that is, we should first understand what Euclidean geometry is. And Euclidean geometry is the study of planar solid figures on the basis of postulates, which are principles, created by Euclid, the Greek mathematician. And Euclidean geometry relies on Euclid's 5 postulates. The first postulate is that a line segment can be drawn between any 2 points. The second is that a straight line can be extended indefinitely. The third is that a circle can be described with any point as the center and any distance from that point as the radius. The fourth is that all right angles are congruent. And the fifth is the parallel postulate, which is the most relevant in hyperbolic geometry. And it's demonstrated in these 2 pictures below. It says that through a given line M and a point P not on that line, there exists only one line, in this case line N, that can pass through point P without ever intersecting line M.
So hyperbolic geometry has a bit of an interesting history. The first mathematician to publish any work on it was named Nikolai Lobachevsky, but other mathematicians were also working on it at the time, including Gauss and Boyer. So the question that they were asking that kind of got to the field of hyperbolic geometry coming about was, what if the parallel postulate, the 5th one that Nisha just described, wasn't true? What if there could be maybe infinite number of lines that could pass through one point, not on a line, and never intersect it? And that's exactly what hyperbolic geometry does.
So like Aaliyah mentioned, the defining characteristic of hyperbolic geometry that makes it non-Euclidean is its refutation or rejection of Euclid's parallel postulate. So in Euclidean geometry, there's only one line that can be parallel to any given line, but in hyperbolic geometry, there's actually an infinite amount of lines that can be parallel to any line. And you can see why this is through this diagram right here. So as you can see in hyperbolic geometry, lines actually are not straight like they are in Euclidean geometry, but rather they are curved. And thus you can then see how there can be an infinite amount of lines that can be parallel to any line, because any line can just continuously bend away and thus never intersect with the line.
So this is just another visual representation of the refutation of the parallel postulate in hyperbolic geometry. So if we look at this blue line here, that's going to be our given line. And then we draw a point right here off of our given line. There is an infinite number of lines that can go through that point that are still considered parallel to our given line. So we can have a line like this or a line like this. And as you see, they can just continue and they're still considered parallel to the given line. And so this may be kind of hard to visualize at first because we typically think of parallel lines as straight lines that have the same slope because we are so used to Euclidean space. But in hyperbolic space, all the lines are curved. And because parallel lines are only defined as a set of lines that never intersect, we know that these are still considered parallel.
So a very important theorem in the field of hyperbolic geometry is the hyperbolic triangle angle sum theorem. And all that really says is that there is no way for any triangle in hyperbolic space to have 180 degrees or more. So it's always going to have less than that.
So before we get into that proof, we need to first familiarize ourselves with the Lambert quadrilateral. And it is defined by its 3 right angles and its 1 non-right angle that is always acute in hyperbolic space. And that is due to the curvature of the lines.
So now that we've seen what a Lambert quadrilateral is, we can get into proving the angle sum theorem. So we see this triangle here, BCA, where we have one right angle here at point C. We can go ahead and put another point here, D, such that we have 2 lines, BD and CA. And then we can go another step and put another line here, FG, that creates a right angle with the lines BD and a right angle with the line CA. And because of this, it's what we call a common perpendicular because of the 2 right angles.
So now that we know that these, also having a common perpendicular makes two lines parallel. So now that we know that the lines BD and CA are parallel, we can say that the interior angles, angle 1 here and angle 2 up here, are equal to each other. Then, going back to what Carissa was talking about with the Lambert quadrilateral, if you look, we see that actually BCFG is a Lambert quadrilateral because it has exactly 3 right angles. And this fourth one here at point B that's made up of angles 2 and 3 is going to be acute. So since we know that angles 2 plus 3 are going to be less than 90 degrees together, and we've also already established that angles 1 and 2 are the same, we can also say that angles 1 plus 3 together are less than 90 degrees, right? And if we have 2 angles of the triangle that together are less than 90 degrees, and we combine them with this right angle here at point C that is exactly 90 degrees, there's no way that that can be 180 degrees or more. So this proves that for all right triangles in hyperbolic space, the angle sum is always going to be less than 180.
So now that we've looked at right triangles, we can now examine non-right triangles. And in Euclidean hyperbolic space, all triangles must have an interior angle sum of less than 180 degrees, which means that there has to be at least 2 acute angles. And in this example, we can say those 2 angles are angles B and C. So now we can see that angle D that's created down here is a projection of angle A onto line segment BC. And a projection is essentially when you drop a perpendicular line from an angle, in this case, angle A, and it forms 2 right triangles because of these right angles here. So now that we have 2 right triangles, like Aaliyah had just proven for right triangles, the interior angle sum is always going to be less than 180 degrees, which means that looking at this first right triangle ABD, these 2 angles A prime and B have to have a sum of less than 90 in order for the entire triangle to be less than 180 degrees. And the same goes for this triangle. Angle A double prime and C have to have a sum of less than 90 degrees in order for triangle ACD to be less than 180 degrees. And since the entire triangle ABC is comprised of these 4 angles, B, A prime, A double prime, and C, then the entire triangle interior angle sum will be less than 180 degrees, proving that for all non-right triangles, the interior angle sum is less than 180 degrees.
So in addition to triangles having angle sums of less than 180 degrees and there being an infinite number of lines parallel to a given line, the curvature that is associated with the hyperbolic plane also makes it unique. So in hyperbolic space, every surface will have negative curvature. So Gaussian curvature specifically describes the curve of a surface at point P and is the product of the 2 principal curvatures known as k sub 1 and k sub 2, and they measure the maximum and minimum bending of a surface at a certain point. So if we have this point right here, point P in the center, these 2 lines or these 2 curves are cross sections of the surface at that point. So the red curve is associated with upward concavity, and that represents positive curvature. And then the green curve is associated with downward concavity, and that represents negative curvature. So if we multiply the positive times the negative, we will always get a negative curvature, which means that this surface exists in hyperbolic space. And so this video is going to show you how they actually found these principal curvatures, just to give you a better visual. But essentially, if you imagine a flat plane going through this surface, that would make this blue plane perpendicular at a certain point. And so you can see that they essentially just slide that plane back and forth to find the 2 principal curvatures. And so there is another formula that we can use to find the Gaussian curvature, and it is oftentimes easier because sometimes it can be difficult to calculate the principal curvatures first before we multiply them. So it is k equals ln minus n squared over eg minus f squared. And before Isaac explains an example using this formula, we need to understand what the answer is going to mean. So if we get a curvature, whether it's positive or negative, that is farther away from 0, it means that it is more curved. So in order to understand a mathematical model of a hyperboloid that we show in a coming slide, we first have to understand the math that goes into finding curvature. And a lot of the math involves multivariable calculus, which may be unfamiliar for some audience members. So I'm only going to touch on the main points of the math, but if anyone is further interested, feel free to ask me any questions afterwards. So in this case, our hyperboloid has a function of z squared equals y squared minus x squared plus 1. And the curvature formula consists of the coefficients of something called the first fundamental form, represented by uppercase E, F, and G. And to find E, F, and G, we first have to parameterize our function. And parameterizing our function just means putting it in a coordinate component form in terms of u and v, which you can see we do right here. So once we have our function in a parameter, we can then take something called the first order partial derivatives of this function, which we do right here. And once we have these derivatives, we can then multiply them together to get something called the dot products, shown here in purple, which also represent E, F, and G. And the curvature formula also consists of the coefficients of something called the second fundamental form, represented by L, M, and N. And to find L, M, and N, we have to find the product between something called the second order partial derivatives, as well as the unit normal vector. And so the second order partial derivatives are exactly what they sound like. They are just the derivatives of the first order partial derivatives. And you can see we found these derivatives right here. And the unit normal vector is a certain vector that is perpendicular to both the first order partial derivative in terms of x and perpendicular to the first order partial derivative that is in terms of y. And the math for solving that is shown right here. And now that we have the second order partial derivatives and the unit normal vector, we can multiply them together to get the dot products shown here in purple, which represent L, M, and N. And now that we have all the values for our variables, we can plug them into our curvature formula to get a curvature of -4 over 1 plus 4v squared plus 4u squared, all to the second power. And we show a model of this. So as you can see here, we graphed our function of our hyperboloid using GeoGebra, and we also created a domain, or U, and a range, or V. And we included negative and positive values for our domain and range. We also inserted the curvature that we found for this hyperboloid. And as I play the video, you can see that no matter what the domain is and no matter what the range is, the curvature for any point on this hyperboloid is always going to be negative, just like the curvature will always be negative for any hyperbolic space. So for a quick recap of what we've talked about so far, we have discussed how hyperbolic geometry differs from Euclidean geometry. So it refutes the parallel postulate. The interior angles of triangles have a sum of less than 180 degrees, and there is always negative curvature in hyperbolic space.
So one application of hyperbolic geometry that we have found is special relativity. And special relativity is essentially the scientific theory regarding the relationship between space and time. And there are two postulates or principles of special relativity that are always constant. And that's that the laws of physics are the same for all inertial reference frames, or that basically means from all viewpoints. And the speed of light is also the same for all inertial reference frames as well.
So the theory of special relativity is only really relevant to apply at very, very high speeds. And by very high speeds, I mean at least 1/10 of the speed of light, which is almost 300 million meters per second. So very, very, very fast. A formula that you'll see a lot in the concerning special relativity is x equals v times t. And that's where x is distance, v is velocity, and t is time. Now, since something exists called the principle of constancy of the speed of light, which is exactly what it sounds like, just that the speed of light is a constant in all inertial reference frames, which, like Nisha said, are basically just points of view. You can always go ahead and replace this variable v for velocity with a constant c that we'll just use to represent the speed of light, since it never changes. So now that we've kind of rephrased this as x equals c times t, c being a constant, that makes t and x, time and distance or length, space, variable and relative to each other. And that means that time and distance can dilate and contract respectively, which is a bit of a weird concept to wrap your head around, that from different points of view, people can experience time and space differently. So in the interest of time, we're not going to go all through examples of that right now. But if anybody has questions about it, I would be happy to explain either of those concepts after our presentation.
So now that we have a basic understanding of what special relativity is, we can now look into Lorentz transformations, which is a subtopic of special relativity. And it's really going to allow you to see the connection special relativity has with hyperbolic geometry. So what are Lorentz transformations? Lorentz transformations represent mathematical models of space-time, and we do this using hyperbolic trigonometry, which will be explained further later. And it's essentially the mathematical relationship between two different frames of reference. So in this case, we can imagine a point A, which represents an event happening in space-time, and this is for a non-moving reference frame, and it's denoted by the x and y axes. So like I just said, it's a non-moving reference frame where A is an event happening in space-time, and we can imagine a photon of light coming to reach A 5 times the speed of light, which is c, in 5 seconds. But for a moving frame of reference, such as a person in a moving car or a moving spaceship, we already discussed that the theory of special relativity says that they're going to experience space and time a little differently, which we represent here with these red lines. So for a moving frame of reference, they're going to experience distance with the x prime axis, and they're going to experience time with the ct prime axis. So to them, event A may actually be happening 2 times the speed of light meters away in around 4 seconds. So you can see it's not exactly linear because this frame of reference is moving. And so then the next obvious question is, how can you jump from one frame of reference to another? In this case, how can you go from point B to point J? And how can you go from point C to point I? And this is where hyperbolic trigonometry comes into play with the use of Lorentz transformation equations shown on this slide. So if angle beta represents the angle between 2 frames of reference, in this case between the x-axis and the x prime axis, as well as between the ct axis and the ct prime axis, you can use this angle beta in your equations to find an x coordinate that corresponds with an x prime coordinate, as well as to find a ct coordinate that corresponds with the ct prime coordinate. And in our equations, we also use something called cosh and sinh. So in Euclidean trigonometry, we're all familiar with using cosine and sine. And in hyperbolic trigonometry, we just use something called cosine hyperbolic or cosh and sine hyperbolic or sinh. And so now you can see how hyperbolic geometry relates to the theory of special relativity and how scientists can then relate the past to the present to the future in a more mathematical sense. So throughout this presentation, we have talked about hyperbolic geometry and its unique characteristics. We started off by defining Euclidean geometry specifically through the use of Euclid's 5 postulates. And we really looked at the parallel postulate because that is actually rejected in hyperbolic space because there are an infinite number of lines that can be considered parallel to any given line. We also talked about how triangles have less than 180 degrees for their angle sums. And both of these principles right here are partly due to the fact that there is always negative curvature in hyperbolic space. We also looked at an application of hyperbolic geometry with special relativity, and specifically hyperbolic trigonometry through the use of Lorentz transformations can be used to relate 2 different frames of reference that experience time and space differently.
So thank you all for listening to our presentation, and especially thank you to our research advisor, Logan, and to all of our classmates for giving us great feedback throughout this process. Good night. Thank you.
All right, we have time for a question or 2.
Yes.
So could hyperbolic geometry be used in like future time travel, space travel?
It does. I mean, okay, so hyperbolic geometry, who knows? I mean, yeah, who knows, I guess would be the question to that, or the answer to that. But in terms of special relativity having to do with that, I could see how it might, but that isn't something that we spent time like looking into. So yeah, that would be an interesting research topic though. Yes.
You were saying how like people experience time differently.
Yeah.
Is that like mentally or like on different sides of the world type situation?
So at very, very high speeds, like I was sort of starting to explain before, and I'm going to try and make this answer not take too long. if you have two people in different, you can imagine two people in different initial reference frames. And what that means is that to one another, it appears that they are still and the other person is moving. Does that make sense? So it could be like a person in a car driving by a person standing on the pavement, right? The person in the car doesn't feel like they're moving, but they're going by and they see the person go by. So it looks like the other person's moving. And the person on the pavement sees them moving in a car and it looks like they're moving. So you have two people in different initial reference frames. I think this explanation is going to go a little bit over the time that I have. So if you wouldn't mind, I'll finish explaining it like after, talk to me. But that's a good question. Anything else or anything on, and nobody's on Zoom? Okay, yeah, cool. All right, thank you.
So continue, right?
Yes.
All right, thank you everybody to come to our random number generator. Before we start, I would like to address named Evan. Evan, not our advisor, but one of our friends who was not here today, but he has helped us with our project. So we want to include his name in our presentation. My name is Hong Tong. I'm Jim. I'm Dylan. All right, so, all right, I want to ask this question. What thing in our life do we usually consider random? If you can give me an example if you want or not. Nice. That's a good one. Yeah. Okay. So a dice roll, like you said, and then flipping a coin. Those are something that we usually consider random. But are they truly random?
So when we look at things like dice rolls and coin flips, a question that typically comes up is, what does it mean to be random? And although there are many types of randomness, today we're mostly concerned with uniform randomness. So we define uniform randomness based on two criteria. First of all, the events must not be predictable, obviously, or else it wouldn't be random. And then secondly, the distribution of frequency of outcomes must be uniform over a set of outcomes. So take, for example, you flip a coin 20 times. If it was uniformly random, you would get 10 heads and 10 tails every time. So this brings us back to our dice and coin flips, which are actually not random because they can be predicted. So if we know the initial conditions before we roll a dice or flip a coin, such as like, the weight, the airspeed, the force with which you flip, you can essentially predict the outcome if you have a strong enough computer. And so this begs the question, is anything random? We say yes, but only on the quantum scale, so like smaller than an atom. Mainly the uncertainty principle, which states that it is impossible to know the position and velocity of any given particle at the same time. So it's a little confusing because we say that if the building blocks of everything can be random, then how can everything else not be random? So now we go to the events larger than the atom.
All right. Let's see. Let's look in our history. Our first attempt at random number generation come from Roman, where they used coin flip to determine outcome of certain situation. But just like Dylan said, coin flip is not actually random. So if you know the velocity or the angle of the way you tilted the coin and the way you flip it, it's not truly random. So it's not random, but many occasions people use it. There was even a story about how Julius Caesar used a coin flip to determine outcome of one of the political debates. So let's look at our next major improvement. Mainly first computer-based random number generator. It was created by a corporation called RAND, where they basically use electronic device or a computer in their time, where they would use this pulse which emit at a random pace, right, like 105 per second, and they would count those number pulses emitted every second. So they will have like 0 and 1, right, every because they use computers, so they have to use binary number. They have 0 and 1s and 0 and 1, like they have it for like so many numbers, and then they will use those number and convert it into digit 1 through 9. And if you convert those, it becomes truly random compared to coin flip, right?
So what about our next major improvement? Let's look at our modern time RNG. We basically nowadays use what's known as pseudo-random sequence. Basically what it does is it creates an algorithm that can generate so many numbers if you have a known C. So if you have a known C and you have an algorithm, it will generate to like millions of numbers that is so hard to predict. But the way you can predict only is that if you have a C and the algorithm, right? So if you're trying to figure out, if you're trying to work back way, it's gonna take you millions years before you can actually find it, because it's just become more and more difficult to find. So what makes new generator better than the old one? It just become harder to predict and become more uniform.
Here comes our uniform randomness test. What it does is, how do we measure the randomness of different random number generators? And we design a test called uniform randomness test, which measure the level of uniformity of a list of random numbers. So the first test we come up with is called relative frequency test. What it does is count the number of frequency each number appears in a list of generation. For example, if you want to generate 4 numbers, 1, 2, 3, 4, and then we generate 40 times. 1 appears 9 times, 2 appear 11 times, and so on and so on. Then how do we calculate, how do we measure the uniformity? That we take the frequency of each value and we find the difference between each frequency with every other frequency. We take the absolute value of it. So, and we sum them together to get D stands for deviation. So this term is x1 minus x2. X stands for the frequency, which is the first value minus the second value, and the first minus the third, first minus the fourth, and so on. So they're all kind of all the possible combinations, and we add them together, which get our in here we get a 6. We already get 6. The closer this value is to 0, the better. Why is it? Because imagine we have a perfectly uniform distribution, and the difference between all of them add together will just be 0, and that's what we want to find. So that's why we call it the deviation from perfectly uniform. And then we have the relative series test. What it is basically a higher dimensional relative frequency test. What does it mean is, instead of taking the frequency of each individual digit, we take the frequency of every pair of digits. So we have generated still the number 1 to 4. But this time we want to extract every 2 digits pairs. There are 16 different combinations for a pair of numbers to appear. There are 1, 1, 1, 2, 1, 3, 1, 4, and so forth. If we graph them into XY plane and then find the frequency of each number appear in the z-axis, you can see in the red bar, then we can plot the frequency for each combination and use them to calculate our d value. And we can also increase them into higher dimension. This is 2 dimension, also to 3 dimension, 4 dimension. The higher the dimension, the more data we have. And the more data we have, the better our test is.
Okay, so now we want to take what Jeff has said and create an equation from that. So our goal, when we look at our example, we have our 16 possible, event outcomes here. And so it's how it's organized is the first event frequency subtracted from every other, then the second across, third, all the way down. And so our equation, we want to not repeat any of the pairs. And so that is represented by the green numbers. These are the ones we want to have. The blue numbers are the ones that equal 0 because we're adding all of them together. So if it's 0, it's irrelevant. And the red numbers are the green numbers that have already been repeated. So for example, x1 minus x2, the absolute value is the same as x2 minus x1. So our equation is a summation equation. So we are taking all of these values and adding them together. So what a summation is, it's a mathematical process represented by sigma, which is the one that looks like an E. And it systematically sums multiple terms of a function. And there are really just 4 parts to a summation. So first of all, there's the sorting variable, which is seen here, and the function. And what it does, it's just like a variable that tells you which numbers you're going to add. The initial index is where you start from. So here, the sorting index is, the initial index is 1, and then we start at 1 and add across. And then our final index is n, and that's where we're going to stop the adding process. And as you can see, it goes to n. So our equation uses two summations, okay? So our first one adds up all of xj minus x1. And when you look at the sigma, j plus 1 and n minus 1 is really just a creative way of excluding the repeats and the ones that equal 0, the repeats, and it stops us at our maximum. And so this equation right here adds up so when you plug 1 into this part of the equation, it adds up these. When you plug into it, it adds up these, and 3, it adds up these. And so after we get the values for however many terms we have, we use our second summation. And this summation describes the first one, which was on the slide we just looked at. And this summation adds the summations that we just made. So you can see here's the same problem we just looked at. So it's x1 subtracted from every other variable all the way to variable number n, and then x2 all the way to n3, and so on. And so we're left with multiple different sums. And now what we want to do is sum all the sums so we get a value that describes our entire set of data. So after all of that, we finally end up with this equation. And what it does is, in its essence, it yields the total deviation from uniform amongst the entire data set.
But there's a middle problem, because when n gets bigger, d can possibly get bigger too. So we want to compare of our d value across different number of generations. We have to find a way to make d independent of n. So how do you do that? How do you make the measurement to be independent of n? We divide the total final value of d by the possible combinations, number of possible combinations of x, j, and xi. What does that mean? If you look at our graph before, here we are generating 4 possible outcomes. So we have 3 plus 2 plus 1. If we have 5 different outcomes, it will be 4 plus 3 plus 2 plus 1. If we have 6, and we'll be keep going on and on. You can imagine there's a very big triangle here, very big triangle. We can sum all the way to n minus 1. We have so if we imagine we are generating with n possible outcomes, and the total combination will be 1 plus 2 plus 3 all the way to n minus 1, which is this summation that stands for. And there's a simpler way to express it, which is n squared minus n over 2. So summary our equation, we define a final measurement, which we denote as m, as the level of uniformity of any set of random number. And as we can see here, which is our d value. And then this one is we divide by the total possible combinations, which we get our m value. And n is the number of possible outcomes, and x is the frequency of each combination. So let's give an example from a previous problem, what it looks like. So you can see this problem before. We already calculated d value equal to 6. Now we divide by the total possible combination, which is 3 plus 2 plus 1. Then we have n equal to 2 times 6 over 4 squared minus 4. We plug in n equal to 4, d equal to 6. Finally, we get 1. It's a very good number because it's close to 0.
All right, so it's bring us to creating our own RNG. Since we've been talking about testing the uniform randomness, we want to create our own random number generator to see if what we say is true. So before we talk about our random number generator, we have to talk about floor function that was used in our random number generator. So basically what floor function does is you take any real number and you round it down to the whole number. So basically, if you have, let's say 7.547, you basically just round it down to 7. If you have like 3.999, it will still round it down to 3. So that's what floor function basically does. So to generate our random number, we have to come up with something, right? So we decided on pi, because pi is irrational number and has a non-repeating decimal. So So we define right here, we define pi function with a variable x, which is gonna give us the x decimal of pi. So basically right here, if you place a, well, let's say we have an x equal to 6, and we're gonna put that into our pi function. Then when you solve it, it should come out as 2. So that's just one generation, right? So how do we create more generation? Then the way we can do it is we have two input, which is the x and generation number, which can be defined as k. So for example, right here, let's say we choose x equal to 3 and we want to generate 4 number at a time. So it's going to be x equal 3 because that's the initial one, and then 4, 5, 6. And then we put those into our pi function. It should come out as 1, 5, 9, and 2, right? So the way we generalized was that if you choose x as any positive integer, and then you're gonna generate k amount of number at a time, where the k is like positive integer, then it should come out as pi x plus 1, pi x plus 2, so on until pi x plus k minus 1. You subtracted 1 because you added 0 at the beginning.
So now comes the question, how do we find x? Because to generate a random number, we have to have a starting point. And we want the starting point to be random also. So we are going to introduce three-body problem. So what is three-body problem? Three-body problem is a mathematical physics problem from 18th century by the French Royal Society. The problem states it's saying that we have 3 stars with equal mass in free space under the influence of gravity. How do we predict their trajectory perfectly? Write an equation that describes the trajectory. So as you can see in this picture, with a very simple initial condition, we can have a crazy trajectory. And actually, in the past 200 years, nobody can come up with an exact solution for the equation. So we're going to use the chaotic nature of three-body problem to generate x value. How we do that? So how do we calculate x? Our generator will have a simulation of three-body problem in the background. And every time we want to generate, we press a button and it will extract 9 data from it, which are the coordinates of each of the stars. We have x1, x2, x3, y1, and so on. And we use these data to calculate the radius, which is distance of each star from the origin. And we multiply those numbers together to get our x value. Because we want to get rid of the decimals, and we want x to be a positive integer, we use the floor function to get rid of decimals. But here's our methodology summary. At the beginning, we have a three-body simulation in the background. And then we extract data from it to calculate x value. Plug x value into our pi function, and then we generate according to our pi function. And how do we want to test how good our generation is? We're going to use the testing method. So here is our generated result. We're going to input it into a function we creating a computer called counter, which count the number of times each pair number or number appears in the generation. We output a list, and then we input this list into our n value calculator, which is the n value we said before in our equation, but this one is a coding version of the n value. So now what we're going to do, we're going to generate 10,000 numbers using our RNG, and we'll test how good it is. So let's see. So here is the code of our editor load the one. Very quick. Okay, here's the code for three-body simulation. So for example, we want to generate x value after 30 seconds. Plug in 30, and here is the list of value and the x value. So when after we press play, we'll see this picture is what happens 30 seconds after the initial condition of our starts. Yeah. And at this instant, the x value is calculated as 34957. So now we're going to plug x value into our pi function. How do you do that? We find an online pi generating decimal generator. We plug the initial starting point as 34957. We generate 10,000 times after the decimal. As you can see, it's our generated result. This is the 10,000 number from our generator. Now let's ask, how do we know this is random? Let's use our uniformity test to find out. Let's copy this number, plug into our counter function. We'll count the number of frequency for each possible combination. So we plug in and we calculate. As you can see here, we separate our entire list of number to two number combinations. We put a comma after every two numbers, basically. And then we count the number of times each combination appears. So we count the number of 0, 0 appears, 61. 0, 1 appears, 43. And there are 100 different combinations and lists are here. So we copy this value and plug into our M value generator. And we calculate the M value, which is equal to 8.66. So how good this value is, we don't know yet, but we are going to compare this value with our Google number generator. So you can see it. This is our generator, DJet. What does it mean? D stands for Dylan, J is me, Jeff, E stands for Evan, and T is Tom. So DJet RNG, our result is close to 8.6. The Google RNG have a result 8.5. So it's very, very close. We're very proud of it. Your sources. And thank you everyone for coming.
Thank you everyone for coming.
Ready? Okay. Hello, people in the Zoom world. Hello, people here. Thank you so much for coming to our presentation today. Now introducing
The Great Frisbee Study. My name is Ash.
My name is CJ.
I'm Shiny.
I'm Toby. So CJ, why Frisbees? Well, basically, we wanted something that was going to be hands-on. We want something interactive. We want something fun. We want something that we can incorporate the GSC student body into, and Frisbees were great for that.
Because that's what GSC is all about. Supporting your friends, right? So the first thing that we have to do is come up with an objective. And basically what we wanted to do is we wanted to take hand tilt and angle of release of some Frisbee throw, use some function, some method, not necessarily the traditional polynomial you know of, but some method by which we can figure out the highest probability region, X and Y, for a Frisbee to land in. So obviously we need to define what angle of release is in the first place. And that is when the front of the Frisbee is tilted upwards, that's a positive angle of release. And when it's tilted downwards, that's a negative angle of release. Of course, how do we measure that? So what we did is upon taking videos of each person and digging through the panels to make sure that we get the scene right before they let go of the Frisbee, what we first do is we take our protractor, right? And with this line on the ground, we make sure that the bottom ray is parallel to that. So we're really truly measuring the angle in reference to the ground. And then we take the vertex of that angle protractor to the very longest edge, most protruding edge of the Frisbee. And then we measure it with the upper ray through the center of the Frisbee. So that's how we get our angle.
And so our second main input variable was hand tilt. And for this, you think about more tilting your hand left or right to see where the Frisbee would go after that. And tilting it down would be a negative tilt, tilting it up would be a positive tilt. Whether that's left or right changes on whether you're left or right-handed. And the way of measuring it is pretty much the exact same, except our reference line here is perpendicular to the old one because we're at a new angle. And again, lining up the reference line here and then passing it through the center of the Frisbee here and getting our value on this protractor of 21.5 degrees.
So now we have our X and Y distance that we need to measure. So after the participant throws, we mark it with the flag, and what we measure is the Y distance from where the Frisbee landed to the origin and along the origin for the X distance. Now, if you're a right-handed thrower, if your Frisbee landed on this side of the origin line, it would be negative. And if it was on this side, it would be positive. And for left-handed throwers, it would be switched because the angles would also be reversed.
We had a few other considerations. First off, we had the same observation site for all of these. All of our trials were carried out right here in the quad in front of the van because this was like the most open area that we could find.
And also we kept the weather as a constant. It was every time we went, it was sunny with low wind speed so that the Frisbee wouldn't blow away. And also we gave everyone clear instructions. We basically said, all right, make sure you throw this casually along the origin line 5 times. Here are some materials we use. We used flags, a tape measure, a Frisbee, which was a Discraft Ultra Star that weighed 175 grams, in case you're interested. We have a Sharpie and 3 smartphones.
All right, so here we're gonna walk you through basically what it looks like out on the quad. First, you have me and CJ over here in the back. We're both recording the two angles that we were using as our input. Here, I was in the back recording the hand tilt of the person throwing right here, and CJ was from the side looking at the angle of release as they throw down this line. And we recorded those videos and then went back and looked at the point at which they released it and find that degree. All right, so circle's a little off, but here's our guy. So basically before they threw, we would record their a little pre-study survey, which would give us information which we sent out to the people in the field for data grouping. And we also recorded their grip and stance.
So after we recorded that information, we had the participant throw a Frisbee 5 times. And each time I would go out in the field and I would mark where it landed with a flag.
And upon the termination of those 5 trials per subject, I would go out and I would measure the distance X and distance Y of the Frisbee and input them into our spreadsheet.
And here's the spreadsheet that we used. You have about 3 seconds to memorize this, take it all in. All right, ready? We're moving on. The end. Thank you for coming. We hope you enjoyed. Just kidding. We have more. So on our first test day, we ran into some problems such as no Wi-Fi, and without Wi-Fi, we can't input data using our laptops. So here's the question. What do you do when you have no Wi-Fi and you need to put in your data?
I don't know why you're looking at me. I don't know.
Any guesses? Write it down.
Hotspot.
Wrong. What you do is you create a bijection between the blades of grass on the ground and the leaves in the tree, and you wait for MathRock to appear. Just kidding. Use the phone.
Yeah, so in our great Frisbee journey, we ran into some great Frisbee problems. The main one being that, tell me, which one of these angles do you think is correct for the Frisbee? Any takers? Left, right, middle?
That's the right.
The right one?
Good answer.
But it's wrong. Because we have no idea. The reason why we have no idea is because we couldn't see the diameter of the Frisbee along which we were actually measuring. We couldn't see the center of the Frisbee specifically. So it's the same situation over here with hand tilt. We're not really sure where the center is. In this photo, it's actually a little more clear, but in most of them, there was so much glare from the sun that we could not tell where the center of the Frisbee was. So
our solution was basically to tape the several axes across the Frisbee. So we were able to measure along these axes in the videos upon review, so we could see exactly what angle it was at and also where the center of the Frisbee was. In addition, we also taped around the parts of the Frisbee that weren't part of the axes, because the Frisbee was like really shiny, as you saw. No offense, shiny, but that was a problem.
So the next big step was to analyze the data that we collected from all the trials. And what we did was, okay, first we're gonna refresh you on like what these variables actually are. So again, angle of release here is tilting up and down. And what we did was we took the angle of release and we compared it to both the X and Y distance separately to see, where we might start finding some correlation. And so these circled dots are from the same throw. So they're both at about 38 degrees of angle of release. And for the X distance, you can see it landed roughly 7 meters away from the origin. And the Y distance was about 1 meter away from the center line.
Words. So here's a refresher about the hand tilt. It's the angle that Toby was capturing from behind the left-right tilt of the Frisbee. And we just proceeded to basically graph it in the same manner with the X distance and Y distance, all in an attempt to find some sort of correlation that we could use to later predict X and Y distance. And here, as you see before, these are part of a trial that we ran on one person, and wherefore the angle or the hand tilt in degrees was 40 degrees. The x distance, right, was approximately 37 meters, and the y distance was approximately 3 meters. Now, if I could go ahead and erase that, can you guys see a strong correlation between the variables?
Say no.
Say no? Is that a no? Yeah. Yeah, neither did we. Look at these R-squared values. This one's in particular is ridiculously low. And R-squared values, basically, what it says is the probability that our hand tilt, our independent variable, for example, is going to be able to indicate our dependent variable, in this case, x distance, and so on and so forth. So in all these relationships, the correlation isn't super strong. So what do?
We make probability grids. So I'm going to walk you through these real quick. What we do is we take a range of degrees. This is for hand tilt and x distance. So let's say this range is from 0 to 8 degrees. We make that column into one group, and we do so for all the different ranges, like 8 to 16 is 16 to 24, and so on. So what we do is we take one column, let's say we have 16 to 24, we count the total number of points within this column, which would be 10, and then we want to find the probability of the Frisbee with a degrees of 16 to 24, anywhere in that range. We want to find the probability of it landing 15 to 30 meters on the x distance. And within this interval, we have 4 dots out of 10. So the probability for the Frisbee landing here in this box would be 4 out of 10. And you may be wondering, why are these boxes so big and why are the intervals so big as well? That's because we didn't have a lot of data and we needed bigger intervals to actually be able to get some reasonable probabilities like these here. And you may also notice that these are small, or not small, but in the mid-range, not too small or not too big. And this is also because of big intervals. And with more data, we could have smaller intervals and more accurate predictions.
And of course, we have to take those experimental probabilities we derived and make it visual for everyone who likes colors, because I like colors. So what we've done is basically we've made hotspots more obvious of Frisbees. So say you have some throw with a hand tilt between 8 and 16 degrees. Based on our experimental data, the x distance is predicted to be within 15 to 30 degrees. And over here on this giant bar, you can see the indication that a probability of 0 is going to have this dark purple color, and a probability of near 1 or 100% is going to have that yellow color.
So what we did was we took the same format and we made 4 different color charts for each of the 4 main graphs we showed you earlier. And this one here is for hand tilt. So again, tilting left and right, and the x distance, which is just straight out from the origin line. And from here you can see, as you increase your degree of hand tilt, the distance from the origin on the x-axis, the probability seems to stay roughly the same across the board. So we didn't think there was very much correlation here between the hand tilt and the x distance, as the probability is pretty even.
And here we have angle of release versus x distance. And when we take a good look at this one, we noticed a slight parabolic trend here. And this might be useful later on when actually analyzing our data more closely and trying to make predictions. So we decided to keep an eye on that as well.
On this graph for angle of release and y distance, there's sort of a correlation here, but we didn't think it was strong enough to try to predict where the Frisbee would land based off of this. So we didn't use it.
So finally, what we actually did use was this rough correlation. Wherefore, if we have some sort of hand tilt that's lower, we expect that it's going to deviate less from that initial throw, that initial line that we throw down.
And so here's just a different representation of all of these graphs. Instead of separating them by x and y distance, here we separate each graph by the range of angles. And then we just multiply the probability of the x distance and the y distance together to give you all these graphs. So you can just see it in a different way of how the degree maybe affects both the y and the x at the same time. And this, of course, was done with the angle of release graphs as well.
Now, the chosen ones. If you remember way back in the beginning of our presentation, we talked about being able to predict the X and Y region in which the Frisbee was most likely to land. So basically, we took our experimental data and we made charts, a little recap. And what we found is that intuitively, we can think of it as an angle of release that's steeper. If you throw it up in a steeper direction, we expect that our Frisbee is not going to travel that far, right? And if we throw it at a shallower angle, we also expect that they probably won't travel as far. And at a moderate angle, it has a better chance of traveling further. But one qualification to make is that we have no mode to measure force, which very likely could be a more significant factor in X distance than angle of release.
So then on to what we use to predict for our y variable. We decided to choose the hand tilt versus y distance because, again, you can sort of see this trend here where if the origin line is roughly about here that they were throwing down, as the hand tilt increased, it seemed to deviate farther and farther from the x-axis. And yeah, that's what we chose for the y.
So the way that we basically fact checked our probability grids is we basically had some people go out and throw, and we matched up like the results with what the grid predicted. So let's say that someone threw and they had an angle of release and a hand tilt of -19 degrees. Well, for the angle of release, that you can see that the 25 degrees would fall into this increment. So that means that the highest probability of where the Frisbee would land would be in this increment of X distance between 30 and 45. So it'd be predicted to land somewhere with that increment. And then their hand tilt is -19 degrees, which we took the absolute value of to get just 19 degrees, which would fall into this increment. So with that increment, the Frisbee would be predicted to land with a y distance between 2.5 and -5 meters, which would be right here. So that's where it'd be predicted to land y-wise. And so combining our predictions for the x and y distance, we get that the Frisbee would be predicted to land right in this interval between -5 and 2.5 meters y and 30 and 45 meters x.
So what we did with this is we tested the grids. We had 6 people come and throw one time each. We took videos and recorded the angle of release, the hand tilt, and the x and y distance of their throw. So over here, we can see one outlier right here, and we had no previous data, so we couldn't compare this to anything to see if it followed a trend. And for all these other points with the angle of release and x distance, we saw that they didn't really follow the trend, which just further proves that force may have been a more significant factor that we just could not measure. And moving on to hand tilt and y distance, we had one outlier here, but we saw that all the other points seemed to follow the trend that we noticed. And we thought this may have been more accurate to say that hand tilt affected y distance more.
So just to recap again, basically we took these variables of hand tilt and angle of release as inputs, and we used them to predict the y distance and the x distance. So hand tilt specifically, y distance, angle of release specifically, x distance, in order to figure out the highest probability region. And obviously these are all our conditional probabilities, as well as from our experimental data. And what this means in effect is that from our data, with hand tilts that were lower, we expected that they would deviate less from line, so we would throw it more straight. And with angle of release that was more moderate, we expected that it could go farther.
So there's a lot of room for improvement with our study. First off, new trials never hurt anyone. Like, more data is pretty much always like a good thing to have. And that would specifically with our study help us get more accurate predictions on our grids because we'd have more throws. And if we got a whole lot of new data, then we could create new grids with smaller increments between like angle of release measurements, like all that stuff. And that would let us more precisely track the path of the Frisbee as it relates to different variables. And also new data could also let us analyze more variables than we did in this study. So that would have been great.
And that brings us to the end of our presentation. We'd like to give a special thanks to Math Rob, our research advisor, for giving us a lot of helpful advice throughout making this presentation and our study.
We'd like to thank Logan and Yvonne for giving us advice impromptu in the lunch line or elsewhere, and for overall being wonderful math instructors.
We'd like to thank Coach Suggs for providing us with Frisbees or with the Frisbee and with cones on the first test day.
Would like to give a special thanks to Mark Zimmerman, who really provided us with the tape measure. We could not have made this long without it.
We'd like to thank Evan for his curiosity in our project, and at one point for being interested in throwing a Frisbee.
And we'd also like to thank our volunteers and participants. Whether we used your data or not, it was very helpful. And without it, we couldn't have made this study or presentation possible. And lastly, thank you to the audience and those of you on Zoom as well. We really hope you enjoyed it. Thank you for coming.
Thanks, you guys.
All right, onward.
I'd like to welcome everyone to our presentation and thank you all for being here. So we'll get started here. What do you think of when you think of waves? So just ponder that to yourself for a bit. But you might think of ocean waves, for example, or you might think of light rays or solar radiation. You might even think of sound waves traveling through the air, those vibrations that we use to communicate. Or you might even think of sine and cosine waves, which you probably used before in math. But did you know that when we take these sine and cosine waves and add them together, they can form a lot of the complex waves that we encounter and use in our everyday life? So I am Braden.
I'm Michael. And I'm Nick, and today we're talking about Fourier series and analysis. But before we even begin, we have to ask ourselves, what is Fourier analysis? Fourier analysis was discovered in 1807 by Joseph Jean-Baptiste Fourier, and he developed the concept of Fourier analysis while working on a propagation problem. The foundation of Fourier analysis is the idea that any wave can be written as the composition of simple sine and cosine waves. Now, this allows us to decompose complex waves and functions into simple, more easily understood components. This concept is used in many different fields, such as mathematics, physics, computer science, and many more that I will touch on later on. But before we even begin to understand the complicated concepts of applications, we need to examine its foundations.
Okay, so the most basic waves that comprise our Fourier series are sinusoidal functions. And these include sine and cosine, like we were previously talking about. These functions are odd and even, but that doesn't really apply to us in that, so we're not really looking into that. What we're looking at more so is where they pass through the y-axis. So you can see here our red wave with our sine function, and it passes through at y equals 0, and our blue wave passes through up here at y equals 1. And that is sort of the basics behind the sinusoidal functions we will be looking at. So before we further examine these functions, we need to know some basic terminology about waves. And some ways we measure waves are period, amplitude, and frequency. So if you take a look at this, first, if you look here on the right, the wave up top has a low frequency and the wave on the bottom has a high frequency. And that's just the number of waves in a given amount of time. So the one up top doesn't have too many, has like 2 or so, and then high frequency at the bottom has a lot more in that same time period. We also have period, which is pretty much the time for the wave to complete a cycle or oscillation, meaning it goes through a complete cycle of crest and trough. And then we also have amplitude, which is pretty much the displacement of the highest and lowest points or crest to troughs from the equilibrium point, which in most cases is the x-axis. And I've been already using these terms, but crest is the top of a wave and trough is the bottom of a wave. So using that terminology we just looked at, we can combine sine waves and cosine waves to create more complex waves. So if you take a look here, we have this red function and blue function, and we combine them together to get this third one, the purple one. And when you look at these, we look specifically at this vertex. And how we add these together is when we take the values of the component waves, being the red and blue ones, at any given point, let's just say at this crest that this orange arrow is pointing, and then we add those values together to create the value for the composite wave at that point, being the purple one. And this, since the crests are the highest points of both waves, this creates the most extreme variation in the wave. And then it's the same is true for all other points, which is why the purple wave is oscillating to more extreme, heights than the blue or red ones respectively. And you can see here's the highest point. Okay, so this also works for more than just a couple waves. We can have a whole bunch of waves of different shapes and sizes. And you could see if you look at the red, green, and blue waves, they add up to get the purple wave. And if you look at this area where they all line up, similarly to the last example, the wave reaches its highest point. And the purple wave isn't just a simple parabola or anything like that. It's a more complex shape because of the positioning of the waves and how adding them at their specific points works. It just makes the wave a bit more complex. So let's take a quick look at an example. So we have 4 waves here. And then these could be either sine or cosine waves. They're all different. They have different frequencies and periods. So if we add all these together here at the bottom, we get the sum of those waves, which creates this more complex, funky looking wave that can be broken down into those 4 components.
Okay, so now we're going to take a look at another example. This is a type of wave called a square wave. It's commonly seen when we're looking at the digital space, particularly because if you'll notice, sometimes we have a value of 1 and sometimes 0, but either 1 or 0. So this is extremely useful when we look at data transfer and in digital applications. The important part about this wave, in case you haven't seen it before, you might notice it's extremely different from the waves that we looked at before. This is not a curvy wave. This wave is not smooth at all. We see we have big jumps here, but we're going to look at how we can use sine and cosine waves to approximate this waves using Fourier analysis. So moving right along, we ask ourselves the question, how can we represent this strange looking periodic wave as a sum of sine and cosine waves? Okay, we have a square wave here. We might start by looking for the average value of this function. And it turns out this is how we'll actually start all of our Fourier analyses. In this case, if we look, we might guess it somewhere around 0. And then if we look at the area above and below the line, y equals 0, the x-axis, we'll notice that it's equivalent. And this tells us that the average value of the square wave is going to be 0. And we denote that with a sub 0 as the average value of our function. And this will be the first step in any Fourier analysis. Moving right along, the next question we might ask ourselves is how the square wave relates to cosine wave. Here you see I've graphed the cosine wave, and we're examining these 2 areas. Below the cosine wave, in this specific section of the square wave, between the cosine wave and the x-axis, the line y equals 0. And what you'll end up noticing is that the area of the blue and the red section here are equivalent. Essentially, these 2 waves are in phase, the square wave and the cosine wave. And so these 2 areas sum to 0, which ends up telling us that there is no relation between these 2 waves. And we can try a different cosine wave, but we'll end up noticing that
it sums to 0, 2, and it turns out that this is a pattern with our square wave. There is no relationship between the square wave and cosine waves. So cosine waves aren't related to the square wave function, but what about sine waves? We have this other tool that we can use. So we notice here, we once again have the case, we have some area located above the line and some located below. But in this case, there's actually a unique differentiating factor, which is that in this section where this blue area is contained, the value of the square wave is less than 0. And what that means is we can actually treat this area as positive because the two line up. Well, one is negative, the other is negative, and so two negatives make a positive. So we're treating that as a positive. And essentially, this means that we now have a positive sum of our two areas occurring over one period of the sine wave. But what can we do with this newfound information? Well, it turns out we can start by creating a one-term approximation. We know that our square wave's amplitude is 1. We're occurring over one period of the square wave, and we derive pi from that, and I'll show you how we get that in just a second. And then we're also looking at the area contained within this sine wave that we looked at on the previous slide. And that ends up giving us the one-term approximation of this function. G of x is equal to 4 over pi times sine of pi x. This pi here has to do with the fact that the period of the square wave that we looked at in the last slide was actually 2. And normally the period of a sine wave is 2 pi. And so in order to account for that distinct difference, we have to divide by pi. We get 2, which matches up with the period of our square wave. And in addition, the area contained within our wave is 4. So that's where that term appears. And then the sine of pi x is simply the square wave or the sine wave that we saw on the previous slide. And so if we graph this one-term approximation, you'll notice that the crests and the troughs begin to line up. This is not a perfect approximation. It's only one term, but we can see that it's doing a pretty good job of lining up with our square wave. But we can end up going further. We can increase the frequency of our sine wave. In this case, if we increase it to 2 pi, you'll notice there's a 2 in our equation for the sine wave now. It sums to 0. And it turns out that for any even number located inside that sine wave, it's going to sum to 0. But for odd numbers, we notice we once again have the case where we have two areas summing to 0 here and here. And then we have these two, which don't match up and represent positive area in our wave. They end up being exactly 1/3 of the previous wave. So the area in total contained here is 4/3. And we can use that information to form a second term approximation. The frequency of our sine wave, obviously, as I said, increased to 3 pi now. It occurs over one period, and where you derive pi from that in the same way that we did with our last wave. And then the area contained within the sine wave is 4/3, which is obviously 1/3 of the previous area we looked at. And we can use this information to form another second term approximation. And you can see where this information is kind of present in this new approximation term. Now, when I graph this term alone, it doesn't look impressive. This looks nothing like a square wave. It's hard to see what this has to do with our square wave. But if I graph them together, if I add them together like we showed adding functions, you'll notice that it actually does a pretty good job of getting closer and closer to approximating our square wave. We see that it starts to jump up and down around the top. And it turns out that we can actually keep going.
But what if we do keep going? Well, we will see that it gets an even better approximation of the square wave with a 3-term approximation. And sadly, that is actually as far as we can go. Just kidding. We have a 4th-term approximation. And as you can see, it is an even better approximation of this little square wave right there. And it's getting even closer and closer to the square wave. But on the end here, we see something called the Gibbs phenomenon, which is just an overshoot of the square wave of the approximation. And if you keep going, you see on the left here, you can see the individual waves we are adding together. And on the right, you see the approximation of the square wave, and it's getting more and more accurate. But this idea of the Gibbs phenomenon does not go away. It goes no matter how far you keep going and how many approximations that you have. But how do we get more accurate results? We use something called summations, and that is just a way to write the sums of many values in a concise way. Summations are denoted by the Greek symbol for sigma. And under sigma, we have n equals 2. It doesn't always have to start at 2, but that's just the starting value. And then that is what you go to above the sigma symbol. It doesn't have to go to 5 all the time. You can go to as high as you want or as low as you want. And n is just the index variable, and it is the expression for each term in the sum. And that is what it looks like after you carry out a summation. But it's important to note that we utilize these using Fourier analysis by summing together and adding together these sine and cosine waves that we are using to try to approximate these waves. And we don't just have to stop at a finite number. We can use it for an infinite number of things, to add an infinite number of things. And
awesome. So now we're ready to begin a discussion of Fourier coefficients. And this is the kind of stuff that Fourier actually wrote about in his 1807 treatise. Now, looking at this information, depending on whether or not you take in calculus, the notation here might look a little bit intimidating, but it's actually fairly simple. And it turns out it's what we just did when we were looking at our square wave example. So in the bottom left, you'll notice that a sub 0 is once again rearing its head. That's just our average value, just as we discussed before. A sub n and b sub n here, these expressions simply relate to how we looked at the area that was contained under the sine and cosine functions to derive those individual terms in our approximation. So a sub 0, once again, ends up being the average value of the wave or function. And a sub m and b sub m are two sequences of values that are going to modify the amplitudes of the waves they correspond to. A sub m will end up modifying cosine waves, and b sub n will end up modifying sine waves. And we can see that if we look at the whole equation of the Fourier series. So this is the general equation of the Fourier series. It still might look very intimidating, but really it's what we just discussed. Our resulting function is going to equal to the average value of the function plus all of our cosine waves multiplied by their respective a sub m terms, plus all the sine waves multiplied by their respective b sub n terms. And so we saw in our square wave example, every a sub m happened to be 0, and our b sub n terms happen to relate to 4 over some number times pi. So the question, how are Fourier series used? Fourier series can actually only be used for periodic functions, but they have wide use in finding eigenvalues for differential equations that have eigensolutions that are sinusoids. But we can also look at the signal analysis where you look at periodic functions. There's a bunch of applications in image processing where you look at continuous patterns, and also some in cell theory. But another question is, how can we go further? And the expansion of this concept into non-periodic functions is really where it gets even more important. So the Fourier transform is another concept of Fourier analysis that allows us to switch between the time amplitude domain and the frequency amplitude domain. And the obvious question becomes, well, what is the frequency domain? If you never heard of that before, it might seem a little bit weird, but we're going to break it down pretty easily. This right here is the waveform of a C major chord. If you're not familiar with music, a C major consists of a C, an E, and a G. But in this case, I've added a D to this waveform. And using frequency domain analysis in the Fourier transform, we can actually break down this wave, which is complex. You would never be able to tell that this is a C major with a D, lacking perfect pitch, just by looking at this wave. Using Fourier transform, we're actually able to break it down into its components and see that this is a C, this represents an E, this represents a G, and this part represents a D. And looking at the x-axis here, we see the frequencies that each of these notes corresponds to, and looking at how long these lines are, we see the amplitude, how much of that sound is present. So this is the waveform of the C major without D. It turns out we can also use this strategy to modify waves. So in this case, I've looked at this frequency analysis, and I've decided I want to pull out this D note. And if you look here on the left, you'll see the wave that has the D inside of it, and on the right, you'll see the one that does not contain the note D. And looking at the frequency domain analysis for the note on the right, you'll notice that the D has completely disappeared. The D note is gone. We just have C, E, and G. And so to finalize our discussion of frequency versus time domains, you might think of the time domain as what you normally see as a representation of waves, but the frequency domain shows us what wave frequencies and at what amplitudes they are present to form a normal time domain wave.
But what can the Fourier analysis be used for in the real world? Well, many people, engineers, have created vibrational dampeners for buildings. In places like California, earthquake safety is a top priority. Fourier analysis is actually used by engineers to make buildings safer with vibrational dampening. Engineers will send vibrations through a building or structure in order to test the harmonic frequencies of the structure, which is how many times the building, sways back and forth until it returns back to its resting position. Then, you can see that right there. They send the vibration through it, and then if you look closely, you can kind of see the building kind of shake and vibrate, which is kind of fun, but not in the real world because the building might fall. Then they use the Fourier transform to decompose the wave and put it into the frequency domain in order to pinpoint and identify the problematic frequencies of the wave that could cause the structural problems within the building. So right here, you see you have the vibrational wave, and then you break it down into the frequency domain, and then with the vibrational dampener, you can, the vibrational dampener will either absorb or alter the wave so that the frequency can pass through the structure unproblematic and will not cause as many problems with the structure. And so if you send it through with the vibrational dampener there, look at the building, nothing, which is good. That's what we want. But you can also use it and auto-tune. Fourier analysis is very good for auto-tuning software. Like Michael touched on earlier, we can use Fourier analysis in order to amplify specific frequencies that we want and kind of mute the other frequencies that we don't want to be heard. In this way, people's voices can be shifted to match specific pitches in music, and many artists use it. I don't know if they know the Fourier part of it, but they do use it. But Fourier analysis isn't just limited to sine and cosine waves. It's also used in facial recognition software, believe it or not. So basically, facial recognition software analyzes a picture of a person's face and finds specific patterns within that person's facial structure that makes them unique. Using Fourier analysis, we can look at the relative amounts of different characteristics in someone's face based off a single image. And then what it kind of looks for is, for example, the vertical distance between the eye and center of the mouth, and the vertical distance between the eyes and the center of the nostrils. And since each person will have a unique frequency of certain characteristics, Fourier analysis allows us to differentiate between their faces. And if it's one frequency for your face or one frequency for your face, it'll be able to identify that based on what it finds in the frequencies using the Fourier transform.
All right, so a quick summary before we wrap up here. So today we went over with you some of the basics behind sinusoidal waves, being sine and cosine, how to measure them, how to add them together, and how that works with different combinations of them. We also went over some of the concepts behind Fourier series and analysis, like taking infinite sums, looking at adding the waves together, and how we can closer approximate square waves. Then we touched on the Fourier transform and frequency time domain to go into more of the practical sort of applications of it and see how this can be also applied to non-periodic functions. And then Nick just went over with us some of the real world applications of Fourier analysis and how it can help us in real life and benefit society. So we would like to give a big thank you to our advisor, Evan, for helping and guiding us through our project. Our fellow math peers who gave us a lot of feedback while we were developing this. And we'd like to thank you all for being our audience.
Good afternoon, everyone, and welcome to our presentation on topology and homeomorphisms. I'm Sarah Helen.
I'm Matthew. I'm Ian.
And I am Aaron. Through topology, we want to show how two shapes are homeomorphic. So imagine a surface made of thin, easily stretchable rubber. You can bend, stretch, twist, and deform the surface any way you want. Just don't tear it. As you deform the surface, it will change in many ways, but some aspects of its nature will stay the same. The aspect of a surface's nature which is unaffected by deformations is called the topology of the surface. The geometry of a surface consists of those properties which do change when the surface is deformed. Curvature is one of the most important geometric properties. Other geometric properties include area, distance, and angle.
Here we have Johann Benedict Listing. Listing was a German mathematician in the 19th century who discovered and introduced the idea of topology. And after the first few decades of the 20th century, his idea of topology will be evolved into the idea of topology. The idea of topological space will be developed.
The word topology is derived from the Greek words topos and logos. Topology deals with the study of the properties of a geometric object that are preserved under continuous deformations. Two objects are considered the same topologically if you can deform one into the other without tearing, cutting, gluing, or other violent actions. For example, a rectangle and an ellipse are both topologically the same as a circle and vice versa. Homeomorphism refers to the continuous stretching and bending of the object into a new shape. If we take an ellipse, we can continuously stretch and bend it to make it look like a rectangle. We don't have to break the shape in any way. Therefore, we say that an ellipse and a rectangle are homeomorphic to each other.
So who introduced homeomorphism? While the idea of homeomorphism would be kind of discovered in 1870, 1880, it won't be officially introduced as an official subject until 1895 by a French mathematician by the name of Henri Poincaré. And then here we have an example of homeomorphism. As mentioned earlier, homeomorphism is the idea of transforming shapes. So here we have a cow in its regular cow form transforming into a sphere.
Sets are what define the boundaries of the surfaces. So each point and boundary on a surface is derived from a set. For example, every point and boundary on this cube is derived from a set. So this leads us into the topic of open sets and closed sets. Open sets are sets that do not have a defined boundary or edge. For example, if Pac-Man were to go over to the right side of the screen here, past this, he would reappear on the left side of the screen right here. This is because there is no defined boundary or edge in this area, meaning it is an open set. And a closed set is a set that does have a defined edge or boundary. For example, if Pac-Man were to go up here and hit this top edge right here, he would stop. This is because there is a defined edge or boundary, making it a closed set.
So this is another example of a closed set. The DVD logo bouncing back and forth in between the screen. So unlike an open set, which has no defined boundaries or edges, a closed set has these boundaries and edges. If this was an open set, the DVD logo would not bounce. It would just go off the screen and come out the other side, but it's bouncing off the edges, therefore it is a closed set.
This animation on the screen is another example of an open set. As you can see, as the crab is moving along his little surface, he is going off the right side of the screen and coming back onto the left side. If this was a closed set, he would not do this, and he would just hit the screen or stop and be a very sad crab. Now, if you're wondering what this particular surface you're looking at is called, it's called a Mobius strip, which is formed by taking a strip of paper or a plane and putting a half twist in it and then connecting the edges. We would have to do that because when we have this kind of shape, we need to connect the arrows to where they line up, so we would have to put a half twist in it. Now, if you're wondering why the crab keeps changing orientation as he makes laps around the screen, keep that in the back of your head because we're going to come back to it.
Open and closed sets relate to homeomorphism because open sets can only be homeomorphic with other open sets. Likewise, closed sets can only be homeomorphic with other closed sets. This is because if you try to morph a shape that is an open set into a shape that is a closed set, there'd be no points on the open set that could map to the boundary of the closed set because there is no defined boundary or edge on the open set. Likewise, if you tried to morph a shape that is a closed set into a shape that is an open set, there would once again be no points on the open set that could map to the boundary of the closed set because, once again, there is no defined boundary or edge in an open set. Another way to show that two surfaces are not homeomorphic to each other is if you have to make a discontinuous transformation to morph one shape into another. For example, if you take a plane and tear a hole in the center to create a donut, which is mathematically known as a torus, these shapes would not be homeomorphic because although you did morph the plane into the torus, you had to tear a hole and create new space. This means that it was a discontinuous transformation.
Remember that a homeomorphism is a function representing the continuous bending and stretching of surfaces.
So how do we show that a function is also a homeomorphism? Well, in order for that to occur, it needs to accomplish 3 criteria. The first is that the function is a bijection. The second is that the function is continuous. And the third is that the inverse of the function must also be continuous. We will go over all 3 of these criteria.
A function is a bijection if it has the characteristics of being both onto and one-to-one. First, you must show that the set is a function. This means that each input is matched with one unique output. What this means is that one input cannot be matched up with more than one output. For a function to be one-to-one, each output must be matched up with one or fewer inputs. And for a function to be onto, each output must be matched up with one or greater inputs. So if a function were to be both onto and one-to-one, each input must be matched up with only one, each output must be matched up with only one input. Think back to the example of an open set being morphed into a closed set. Because there are no points on the open set that can map to the border of a closed set, the function would not be a bijection.
This brings us to our second criteria, which is continuity. So for our purposes, a function is defined as continuous when it does not have any large changes in value between points and all points on the domain exist. Take this function below where Gandalf has very generously created a vertical asymptote for us to demonstrate. If we take a point directly to the left and a point directly to the right of the asymptote and then plot them, we can see that the resulting values are in fact extremely far apart, and therefore we can say that this function is not continuous. So how are we going to relate this to our concept of topological spaces? Well, let's take the square and circle example from earlier. I have composed them in this manner on the screen, but they can really be composed in any manner. So the first observation that we need to look at is that there's always a maximum finite distance between the boundaries of the circle and the square. So there's no edge going off into infinity that goes off the screen. So this is important because we can then observe that points that are close to each other on the circle are also close to each other on the square. Therefore, we can say that this would be a continuous function.
In order to prove that the inverse function is continuous, you must be able to morph a shape into another shape in a continuous way, and then morph that shape back into the original shape again in a continuous way. For example, you were able to morph a square into a circle in a continuous way. This means that the function is continuous. You are also able to morph the square back into morph the circle back into the square in a continuous way. This means that the inverse function is also continuous.
All right, so if looks don't matter, how are we going to show that 2 shapes such as this really are different? We see some lines, there's different edges, but how do we do it? Well, I've put together a little example for us that'll demonstrate this point. So here on the square, we have Math Rob. He's preparing for an epic competition and he needs to practice. So he's going to begin by running across the square until he gets to an edge. He's then going to run around the edge of the square until he gets back to his original starting position. As you can see, he makes one continuous loop. Now, what if Math Rob were on a shape such as this disk? Well, he'd begin in the same way. He'd run until he meets an edge. He would then try to run around the edge until he gets back to his original point, but oh wait, he crosses his own path and then must follow it back to his original starting position. Now let's compare. In the example of the square, his path did not overlap itself, where in the example of the disk, it did. This is how Math Rob is going to tell the difference between these 2 surfaces, and it has nothing to do with how they look. They are really different.
A surface is a visual representation of a mathematical object that is composed of deformed planes. Now, all this means is that you are able to take a plane and morph it into a shape. For example, To create the sphere on the right side of the screen, you could take a flat plate and blow it up like a bubble, thus creating the spherical shape. And for the shape on the left, you are also able to take a flat plate and morph it into that shape. Now, this is true for all shapes, such as spheres, cubes, and tori.
So for our purposes, the surfaces we're exploring meet 3 criteria. Connected. A connected surface is a surface from any point of which a continuous path can be drawn to another point without crossing its boundary. Since the surface is one continuous piece, 2 tori interlocked together would not be an example. Closed. A closed surface is a surface that has no boundary or rim and it is compact, meaning that it has a finite number of holes. If you cut the torus in half, you would create a rim. Therefore, it would not be closed. And triangulable. Triangulable means that we can chop the surface into a finite number of vertices, edges, and bases.
We can now start classifying some shapes.
So next we have Leonard Euler. So Leonard Euler was a mathematician who created the Euler characteristic or Euler number in classifying surfaces. How we would get the Euler number is we would take the number of vertices, subtract the number of edges, and add how many faces there are in a shape. Or to simplify it, v minus e plus f.
The picture above shows a sphere on the left and a 2D map with orientations on the right. The 2D map has one face, 2 edges, and edges that will be connected together are shown in one color, and 3 vertices. Vertices that are the same color are the same.
In order to illustrate how this 2D plane could in fact be a sphere, we've made a video for you. So we're going to begin by lining up the edges that are the same. So the blue to the blue and in this case for the video, the pink to the pink. And since we can't stretch the paper, we cut it, but we're not doing that in our theoretical realm. So we've lined up our edges with the blue to the blue and the pink to the pink, and now we have a 3D conical shape. We can then take this shape and inflate it into a sphere. Wow, look at that. That's how it's a sphere.
So 3 vertices minus 2 edges plus 1 face equals 2.
So the left projection is a 2D map of a torus. If we align the edges, we would form the torus. We need to count the edges and the vertices that are the same, and those are shown in the same color. So first we would fold together the red edges because they're the same edge. And then we would take the blue edges and fold them together and we would form the torus. And then from there we just find the Euler number. We look at how many vertices there are, which is just 1. How many edges? There's 2. And there's only 1 face. So 1 minus 2 plus 1 equals 0. The next we have the double torus. We begin with a single torus, and the projection is just like the last one, except an extra edge is added. The edge disappears at the end, preserving the homeomorphism. We would then essentially glue 2 tori together to form the double torus. And then from here, it's just the same thing that we did on the first one. We look for how many vertices there are, which is 1. There's 4 edges, and there's only 1 face. So 1 minus 4 plus 1, we get -2.
This shows a pattern for calculating the Euler number of surfaces based on however many holes this surface has. For example, a sphere with 0 holes has an Euler number of 2. A single torus with 1 hole has an Euler number of 0. The double torus with 2 holes has an Euler number of -2. This continues on based on however many holes the surface has. What this shows us is that in order to calculate a surface's Euler number, we use formula 2 minus 2 times however many holes a surface has. So any closed orientable surface can be classified as being homeomorphic to either a sphere or a sum of tori based on however many holes the surface has. For example, this pretzel has 3 holes. So can anyone guess what shape this would be homeomorphic to? If you said a triple torus, then you would be correct. This is because a pretzel has 3 holes and a triple torus also has 3 holes.
if one of the words Matt just said from the last slide is unknown to you, that's okay because I'm going to explain it now. So it turns out that we actually have one more distinction about our surfaces that we need to make before we can classify them, and that's orientability. So up until this point, the surfaces that we've classified are orientable. That just means that there is not a Mobius strip in the 2D map of the surface. So a non-orientable surface just means that there is a Mobius strip somewhere. So recall back to the crab animation and how every time he made a round across his surface, he came back facing a different direction. You could say he was disoriented. Well, that's why. And any surface that has a Mobius strip will take on the same characteristic. In contrast, if the crab were walking around on, say, a sphere, it doesn't matter where he goes, he will always come back facing the same direction. And so it turns out that we can't quite calculate the Euler number of non-orientable surfaces in the same way, but it is possible. Just instead of using tori, we have to use projective planes. Now, a projective plane is a really abstract concept that we don't have time to flesh out in detail, so I'll just give you the basic construction. Let's take this plane on the left. Like before, we're going to try and match up the edges that are the same together. So let's start with B, and because the arrows are facing opposite directions, we have to twist it around to connect them. And we create this Mobius strip as seen. Now here comes the hard part. We would have to do the same thing to the other set of edges. Twist the A around and connect it to the other A. But when we made the Mobius strip, we have one continuous edge. So we would basically have to take this half of the edge and somehow twist it and perfectly connect it with this other half of the edge. Now, this is not possible in 3D space because it would self-intersect. And if you're confused about what this may look like, don't worry, you're not alone. No one can really come up with one 3D visualization of this plane. Here are a few different versions. I myself like the one on the left because it reminds me of a fortune cookie, but you can pick your favorite. So to summarize, the way we calculate the Euler number of a non-orientable surface turns out to be 2 minus the number of self-intersections of the surface, which I have given the variable n. So Euler number equals 2 minus n.
One example of a non-orientable surface is called the Klein bottle. Now, if you take the Klein bottle and cut it in half, you will come out with 2 Mobius strips. So what this means is that the Klein bottle has 2 self-intersections. So in order to calculate the Euler number of the Klein bottle, you would take 2 minus 2, which equals 0.
Next we have surface classification theorem. We've just learned what it takes to show surfaces are the same through the surface classification theorem. Any closed surface is homeomorphic to one of these surfaces, being a sphere, a connected sum of tori, or connected sum of projective planes.
Now that we have mastered the surface classification theorem, you can now determine when two objects are the same. For example, if we calculate the Euler number for this cow, it would be 2. This brings us to the end of our presentation about homeomorphisms and surface classification. We hope you now view mathematical and everyday objects in a new way.
At this time, we just like to thank our instructor and advisor for the past 5 weeks, Math Rob, for helping us really understand our concept and form our presentation, as well as all the other math faculty and research groups that have provided invaluable feedback for our presentation. And we'd like to thank you, the audience that came in today to view our presentation. We hope you enjoyed it. And we also like to thank the people on Zoom that also came, because wherever you are, you took some time out of your day to come see our presentation. And we're very thankful for that. Thank you, guys.
Yes, please go ahead. Yes.
Hello and welcome everyone. My name is Abby. I'm Yvonne.
And I'm Marv.
And our research project is the universal flight operation. We studied the math behind how airplanes work and then mapped their trajectory.
Our big question is, how do planes work? Before the pandemic, approximately 176,000 flights departed every year. This process allows us to efficiently travel lengths and speeds that had never before been possible. The study of aeronautics depends on mathematical principles, without which an airplane would never be able to lift off the ground, let alone safely. There are 4 primary forces that make this possible, and they are lift, weight, thrust, and drag. But before we get into that, here's a brief overview of our model plane and the variables that are involved. Here you can see our gravity, which will remain consistent at 9.8 meters per second squared. Our plane will reach its cruise speed at an altitude of 30,000 feet. The total airspeed will be at 400 knots, which translates to a velocity of 206 meters per second. On the right, you can see a blueprint of our wing, where the total area is 2,767.5 feet squared, or 843.5 meters squared. And on the bottom right, we drew a male human that is drawn to scale.
Our first force to look at is lift, which is responsible for keeping the airplane aloft. So the object depicted here in the center is the wing of a plane, and as air travels from the right, it splits into two groups, where air above the wing is going at a faster speed and therefore has a lower pressure, whereas air below the wing is going at a slower speed and has a higher pressure. This generates a force that pushes the wing upwards and keeps it in the sky. And we can calculate lift using the modern lift equation shown here in the bottom right. Our first variable here is CL for the lift coefficient, which is a dimensionless quantity, and it measures the relationship between a difference in pressure and our lift. And next we have R for air density, which is the atmospheric mass per unit volume. Then V for our velocity of the plane, which is sometimes called true airspeed, and it's relative to the air mass. And lastly, we have A for the area of the wing face. So before we can solve for lift, we first have to solve for our air density, which is represented by this formula in the top left. And assuming that we're at cruise altitude, we can use the average pressure and temperature, represented as P and T here, at that height, and substitute those values in to get a total air density of 0.4589 kilograms per cubic meter. And then moving over to the right side here, we have our lift coefficient, and we run into a problem because lift is one of the variables in the equation for lift coefficient. So to understand this, we have to know the difference or the relationship between lift and weight. When an airplane is on the ground, its weight is greater than its lift. And then during takeoff, there's a midpoint where lift and weight are equivalent. And then at cruise height, our lift will be greater than our weight, allowing it to fly. So here we have to assume that our lift and weight are equivalent. And using that value, we can substitute all that we already know because we just found our area, air density, and velocity, and get a lift coefficient of 0.4871. And then using those values, we can finally find our lift, which would be 4,157,477 newtons.
Okay, so the next of our four forces is weight, which is the gravitational attraction of the plane to Earth. It counteracts lift as it pulls the plane downwards. Here's the general equation for weight, where m is mass and g is gravitational acceleration. For those of you who don't know, mass is the amount of matter that makes up an object, whereas gravitational acceleration is the acceleration of an object as gravity is pulling it towards the center of mass of a more massive object. So in the context of plane flight, gravity is pulling the body of the plane towards the center of the Earth. Yep. And here is what we get when we plug in the statistics of our plane into the weight equation, where we put in 408,000 kilograms for the mass, and we use 9.8 as the gravity of Earth. And when we plugged it in, we got 4 million newtons. And this is significant because it's less than the lift of the plane that we calculated earlier, which means that in this case, our plane would be able to fly. Yay.
Thrust is the force responsible for moving a plane forward. It is generated when air is pushed to the opposite direction of the motion. Airplanes use propeller engines, which utilize a turbine blade that spins and forces air backwards, causing the plane to move forward. The thrust generated not only has to balance the drag of the airplane, which counteracts thrust, it has to exceed it in order for the airplane to accelerate. Thrust can be calculated using this general thrust formula, where the mass flow rate refers to the rate of the movement of the air. The free stream refers to the air that is unaffected by the aircraft, and exit refers to the air that is affected by the aircraft. This formula is used to calculate the total amount of thrust produced from any type of propulsion system. And so since different airplanes use different types of engine, this formula can be modified accordingly. Our model airplane utilizes a turbojet engine, which uses a nozzle that equalizes the exit pressure from the free stream pressure. And so this part of the equation is canceled out, leaving us with this revised equation: mass flow rate times the exit velocity minus the mass flow rate times the free stream velocity. And it can be broken down into two parts: gross thrust and ram drag. Gross thrust is the total amount of thrust produced without the reduction of ram drag, hence why this is subtracted out. And up here, you can see a diagram of our turbojet engine. And to briefly describe how it works, the surrounding air, also known as the free stream velocity, is brought into the inlet where it meets the compressor, where the compressor squeezes the air into smaller areas, causing the air pressure to increase. The burner then extracts, the burner applies a small amount of its fuel, turning the air into hot exhaust, where the turbine extracts some of that energy and uses it to power the compressor. And it also uses it to turn its blade, forcing the air towards the nozzle, where it will pass through at a much higher air temperature and pressure than initially was. And then we refer to this new air as the exit velocity. Once air leaves the nozzle, thrust is generated. To calculate thrust, we must first revise the equation to the mass flow rate times the exit velocity minus the free stream velocity, because the exit mass flow rate and the free stream mass flow rate are nearly identical. And so the difference between the two is insignificant. To find the mass flow rate, we can multiply the air density, the velocity, and the cross-sectional area of the, cross-sectional area of the inlet. The air density was found earlier by Abby, which was 0.4589 kilograms per cubic meters. The velocity was predetermined, and now we have to find the area of the inlet. Since the inlet is circular, we can use the formula pi r squared to find the area. Here you can see that the diameter is 94 inches. We divide that by 2 to get a radius of 47 inches. And when we plug that in, we can get a total area of 6,940 inches squared. However, the mass flow rate requires all the units to be in meters. And so we have to convert that into 4.4 meters squared. And now we multiply that with the air density and the velocity to get a mass flow rate of roughly 416 kilograms per second. And finally, we multiply that to the difference between the exit velocity, which is 1,522 meters per second, and the free stream velocity to get a total force of 547,386 newtons.
And the last force we'll look at today is drag, which is an object's resistance of motion through a fluid. So in our case, the plane's resistance of motion through the air, and it will counteract the thrust by pulling the plane backwards. At the bottom of the screen here, you'll see that we have our drag equation, which is very similar to our equation for lift. And the only difference is the coefficients in the front. And because of this, the two forces are directly proportional. So as lift increases, so will our drag, and the same thing goes vice versa. Out of these three shapes, which do you think would have the lowest drag coefficient? Any guesses? The middle. Good guess. We'll test that hypothesis. So our square has a drag coefficient of 1.05. The rhombus is 0.8. And in the center, it drops all the way down to 0.04. So good job, you are correct. This object in the center is actually referred to as an aerofoil, and it's been designed and perfected to be the most aerodynamic shape for the wing of our plane. To calculate the drag, we use the same variables before with lift, but we have our new drag coefficient, and we get 341,406 newtons, which is less than our thrust, so the plane would be able to propel itself forwards.
Fluid dynamics describe the motion of fluids, which include both liquids and gases. Because we're going to be focusing on the movement of airplanes through the air, we're going to be focusing on a subsection of fluid dynamics known as aerodynamics. One of the most important principles of aerodynamics is Bernoulli's principle, which essentially states that fluids that are moving more slowly have higher pressures and then compared to fluids that are moving more quickly. So the shape that Abby showed you earlier, known as the aerofoil, works really well because the top is curved, the air moves more quickly over it, and this creates a lower pressure compared to the bottom, where the air has to move a shorter distance, and so it builds up a higher pressure. The differential of the pressures causes the lift to be created, and the wing rises up.
And here you can see we use Bernoulli's equation to calculate what difference in pressure we would need to generate enough lift. So everything on the left side of the equation here represents air that's going below the plane. And then everything on the right side here is air that travels above the wing of the plane. So we have two terms at the end of each set, RGH, sub 1 and sub 2. And those measure the relative height of the air at either point. But because the wing of the plane is only about a meter thick, it will have a minuscule effect in the end result of our equation. So we can start by canceling these two terms out. And then once we do that, I rearrange the equation so we would have our difference in pressure on the left. And we can factor out 1/2 r from either side of the equation and substitute our values from earlier. Now for velocity, we decided to test two different airspeeds to see if that would generate enough of a pressure difference. So this means that the air above the wing is going 200 miles per hour and the air below the wing is going 150 miles per hour. And then once we do that, we can calculate the difference in pressure to be about 4,000 newtons per meter squared. And then we would multiply that number by the area of the wing and get a necessary force of 3 million newtons. But we have a problem because our lift was over 4 million newtons. So this difference in speed would not create enough pressure for lift. To find out exactly how much of a pressure difference we would need, we can add our value for lift right here and solve for delta P, which would be 4,928 kilopascals. So that number just represents the difference in pressure that would be necessary for lift. And now that we have our 4 forces down, we can move on to modeling the trajectory of our plane. So we need to figure out at what point to begin descent and what curve to follow for a safe landing. We have to consider 4 different constraints, which are the initial descent position, horizontal dips instead of deep dives, because when a plane initially begins its descent, it starts horizontally instead of angling downward, so to protect the cargo and passengers. And then our third point here, the aircraft lands with an angle of attack of 0, just means that the plane will be parallel with the runway, this. And the landing concludes at h equals 0, so when the height of the plane is 0 and it's hit the ground. And this video will do a good job of describing the trajectory I was mentioning earlier.
To model an aircraft trajectory, it is important to discuss its speed. An aircraft's speed can be heavily affected by the wind. So that is why we must consider the 3 different types of speed, which are ground, air, and wind. Ground speed is the speed of the aircraft while it is on the ground. Air speed is the speed of the aircraft while it is in the air. And wind speed is the speed of the actual air surrounding the aircraft. The relationship between these 3 types of speed can be found using the formula ground speed equals airspeed plus wind speed. And this all ties into vector quantities.
All right, so vectors are quantities that have both magnitude and direction. Now, when we're considering the movement of a plane through the air, it's important for us to consider both the direction that it's going in and its speed or its magnitude. So vectors are, because of this, vectors are a very good way of representing the movement of a plane through the air. So vectors are usually represented as arrows on a plane, where the bottom right here is known as the initial point, and the arrowhead right here is known as the terminal point. The direction of the vector is indicated by the line that you make going from the initial point to the terminal point, and the magnitude of the vector is essentially how long it is. Vectors are usually represented in component form, which is similar to the ordered pairs you've probably learned about in school. The only difference is that component form describes the differences in the initial point and the terminal point on the XY plane. So vectors can be added together. In the context of aircraft flight, this can express how the velocity of the plane is affected by external force, such as wind. So what happens when a plane in flight hits a crosswind? Vectors can tell us the answer. So in our situation, an airplane is cruising along at 475 miles per hour due east. A wind blows from the southwest at 50 miles per hour. We need to find the ground speed of the airplane. So here is our diagram with all the information we've been given filled in for us. We know the angle is 45 degrees because the wind is coming from the southwest direction and it is going directly in between both north and east, which is a 90-degree angle, so half of that is 45 degrees. We know that the speed of the plane is 475 miles per hour, and we know the wind is 50 miles per hour. All right, so the red arrow here is the resultant force, or it's going to be the new speed and direction of the plane after we've calculated how the wind has affected its motion through the air. We can find the resultant force by adding together F sub 1 and F sub 2, which respectively represent the movement of the plane and the movement of the wind. Now, we already know what F sub 1 is in component form since the plane is moving directly along the x-axis and yeah, it's moving in a straight line. So we need to find F sub 2 in order to get our F sub r value. In order to find our F sub 2, we just use this equation, which looks a little bit scary, but all we're really doing is finding the distance that the length of the vector is in both the y and the x directions. It's where we use sine for our y distance and cosine for our x distance. So once we plug in all the numbers, we ultimately get 35.36, 35.36 as our component form for F sub 2. Now that we have that, we can add it to our F sub 1. And when we do that, we get 510.36, 35.36. Now, this is a new speed and direction of the plane, and that doesn't make a whole lot of sense in context. So what we need to do is find the magnitude of our F sub r vector. In order to do that, we use this equation. We just use the values from our F sub r component form of the vector, and we get 511.6 miles per hour as the new speed of the plane. This is relevant because it shows that the plane actually sped up once it hit the wind.
And one important distinction to make here is the difference between curves and trajectory. So in our real world applications, we have trajectory because we have two endpoints, the origin of descent and our final destination. But when we do mathematical models, we have to assume them to be a curve, which is a continuous line. And in our graph here, the horizontal axis is L for lift, and the vertical axis is lowercase h for height. And what's interesting here is the location of L actually represents the line where lift and weight are equivalent, like I was talking about earlier. So everything to the left is negative and everything to the right is positive. And in the top left, we have our initial descent position. Now to graph this, you can't use a linear function because it's not a straight line. And we can't use a quadratic function because a parabola wouldn't meet our constraints from earlier. So we use a cubic function, which is represented by the blue line. And then to transform the graph to match our descent pattern, we can make our A and C coefficients negative to get the line in red. And once we do that, we get this equation right here. And then when x is at negative L, comma, capital H, that just represents the peak height. And then we can take the derivative of this to find the slope of that point of the curve. And then on the left side, we have to assume that the plane is now on the ground, so C and D are both 0. And then rearranging those equations, we can find the values of all of our variables, which would be substituted back into our original cubic function. And once we do that and simplify, we find the approximation curve of the plane to be 2hx cubed divided by L squared plus 3hx squared divided by L cubed. So this complicated formula just means the curve of the line that we would have to follow.
So to summarize, we have discussed the 4 forces that make flight possible, which are lift, weight, thrust, and drag. We have also covered fluid dynamics and how it involves Bernoulli's principle, as well as how speed and vectors relate to an aircraft's trajectory. We wanted to thank the math department and our fellow peers for their constructive feedback, as well as our math advisor, Logan, for everything she has done to help us. We also wanted to thank you, the audience, both in person and on Zoom, for watching.